Have you ever wondered what stories the night sky could tell, if only we knew how to listen? The universe does not shout, it whispers, it echoes. Every explosion, every collision, every star's first breath leaves a ripple in the fabric of existence. Even now, the cosmos hums with the memory of ancient events. We live surrounded by messengers from the distant past, light that left galaxies millions of years ago, radiation born in the universe's infancy, vibrations from catastrophic collisions that happened billions of years before Earth existed. Tonight, we listen, not for new sounds but for old ones, still traveling across the deep. This is a universe made of echoes. This is the story of how everything that has ever happened continues to reverberate through time and space, carrying whispers from the beginning to the very end. What is the oldest thing your eyes have ever seen? Perhaps you think it's an ancient tree, a mountain range, or maybe a fossil. But every night, your eyes capture something far more ancient: starlight. When you gaze upward on a clear night, you're not seeing the stars as they are now, but as they were when their light first began its journey toward Earth. Light is the first and most fundamental echo in our universe. Every photon carries with it the memory of its birth. The photon that formed inside the heart of the sun takes thousands of years to reach the surface, and then just 8 minutes to reach your skin. But photons from distant stars take far longer journeys. The light from Proxima Centauri, our nearest stellar neighbor, travels for 4 years before reaching us. The light from the Andromeda Galaxy has been traveling for 2.5 million years. Imagine that. The photons striking your retina right now left their source when early humans were first learning to use stone tools. Those ancient humans never knew these photons existed, yet here they are, completing their epic journey across space, carrying information from a time long before written history. This light stretches and fades as the universe expands. The wavelengths elongate, shifting from the brilliant blues and whites of young stars to the deep reds of aging light. We call this cosmic redshift. It's as though the universe is taking a deep breath, and all the light within it stretches in response. The most distant galaxy we can see, GNZ 11, appears to us as it existed 13.4 billion years ago. Those photons began their journey when the universe was just 400 million years old. They've traveled 32 billion light years due to the expanding fabric of space, carrying the memory of stars that likely burned out billions of years ago. Every beam of light is an ancient messenger. The stars you see tonight might not even exist anymore. Many have already exploded, collapsed, or faded away. But their light continues onward, a ghost of their former existence, still traveling through the void. Think of it this way. If an alien 65 million light years away pointed a powerful telescope at Earth right now, they wouldn't see us humans. Our present moment is already racing outward at the speed of light, an expanding sphere of information that will someday reach distant worlds and distant times. And just as those future observers would see our past, we are perpetually watching the universe's past unfold before our eyes. The night sky is not a canvas of the present, but a window into history, a collection of moments from different times, all arriving simultaneously at our tiny planet. Even the sun you see is already 8 minutes old by the time you perceive it. The light that warms your face on a summer day was born in nuclear fusion reactions that happened while you were doing something else entirely. Perhaps you were still asleep when those particular photons began their journey from the sun's core. And this delay, this gap between event and observation, grows larger with distance. The farther we look into space, the deeper we peer into the past. Astronomers don't need time machines. Their telescopes already serve that purpose, capturing ancient light from across the cosmos. Every beam is a time capsule, every photon a historical document. The universe preserves its own history in the form of electromagnetic radiation, still traveling outward from every event that has ever occurred. We live surrounded by these echoes, these whispers from the distant past, carrying stories across billions of years to reach our eyes at this precise moment. Light reveals not just what objects look like, but what they looked like. When astronomers observe a supernova 100 million light-years away, they're not witnessing a current event, but a spectacular explosion that happened when dinosaurs still walked the Earth. By the time we see it, the actual remnants of that explosion have had 100 million years to cool and disperse into space. This strange relationship between light and time means our universe is a landscape of temporal illusions. What appears simultaneous to our eyes actually happened across vast stretches of time. The stars in a single constellation may be separated by thousands of light years, their light reaching us from vastly different eras. Consider this. The light from Deneb in the constellation Cygnus left that star 1,500 years ago. The light from Altair in the same night sky left just 17 years ago. When you observe both stars in a single glance, you're seeing Deneb as it was when the Roman Empire was falling, and Altair as it was when smartphones were becoming popular. These vastly different moments in time appear to us as a single coherent night sky. How strange to think that somewhere, 30 light-years away, Earth appears as it did in 1995. 50 light-years away, World War II hasn't happened yet. 100 light-years away, the Wright brothers haven't flown their first airplane. 2,000 light-years away, human civilization is just beginning. And all these moments continue to travel outward, preserved in the light that carries them away from Earth. Light also changes as it travels. The expansion of the universe stretches its wavelengths, shifting colors toward the red end of the spectrum. The more distant the object, the greater this redshift. For the most ancient light in our observable universe, this stretching has been so extreme that visible light has been pulled into the microwave range. We'll explore this cosmic microwave background in our next chapter. But light does more than just travel. It interacts. It bounces off surfaces, gets absorbed and re-emitted, passes through clouds of gas and dust. Each of these interactions leaves its mark on the light, altering its spectrum, its polarization, its intensity. By the time light reaches our telescopes, it carries not just information about its source, but about everything it encountered along its epic journey. Astronomers are cosmic detectives, reading these subtle changes in light to learn about distant objects. When light passes through a planet's atmosphere, certain wavelengths get absorbed by gases like oxygen, methane, or water vapor. This creates a distinctive fingerprint in the light spectrum. By analyzing these absorption lines, scientists can determine the composition of planets orbiting distant stars without ever visiting them. This is how we know that exoplanet HD 189733b has a blue atmosphere containing silicate glass that rains sideways in 5,400 mile-per-hour winds. We know that Kepler 442b might have clouds made of ruby and sapphire particles. We know all this because light carried the information across trillions of miles of space, preserving it for our telescopes to capture. Some of the light reaching us has taken truly extraordinary journeys. When light passes near massive objects like galaxy clusters, its path gets bent by gravity, creating cosmic lenses that can magnify distant objects. Through this gravitational lensing, we've observed galaxies so far away that their light has been traveling for over 13 billion years, from when the universe was just 3% of its current age. These ancient photons are messengers from a time when the universe was very different. Hotter, denser, more chaotic. They've traveled across nearly the entire observable universe to reach us, carrying information about how galaxies formed in the cosmic dawn. Every photon reaching Earth has survived an improbable journey. It had to avoid being absorbed by dust, gas, or other matter for billions of years. It had to navigate the expanding fabric of space, traveling through a universe that was changing around it. Against all odds, it arrived precisely at the moment when humans developed the technology to detect and appreciate it. In a very real sense, light is the memory of the cosmos. It remembers events long after they've ended. It carries information about stars long dead, explosions long faded, and worlds that may no longer exist. When we look up at the night sky, we're seeing not just distant objects, but distant times, all arriving simultaneously to paint a picture of a universe that was, rather than a universe that is. And this is just the beginning of our story about cosmic echoes. Light is merely the first and most obvious echo in a universe that preserves its history in many forms. As we journey further, we'll discover that the cosmos whispers its secrets to us in many voices, some obvious, some subtle, all carrying echoes of the distant past across the endless expanse of space and time. What would it be like to hear the very first sound the universe ever made? To capture the initial whisper of existence itself? An echo so ancient, it predates every star, every planet, and every galaxy we can see. This is the cosmic microwave background, the oldest light in the universe, the first whisper of creation itself. To understand this remarkable echo, we need to travel back to a time before anything familiar existed. In the beginning, immediately following the Big Bang, approximately 13.8 billion years ago, the universe was unimaginably hot and dense. So hot that no atoms could form. So dense that light could barely move. The entire cosmos was a seething plasma of elementary particles. A soup so energetic that photons, the particles of light, could only travel microscopic distances before colliding with electrons. Imagine this moment. The entire observable universe compressed into a volume smaller than our solar system. Every point in space touching every other point, with no distinct structures, no emptiness, just pure, raw energy and fundamental particles in a chaotic dance. The temperature was in the trillions of degrees. This was not a universe of stars and planets, but a universe of pure potential, a cosmos still in its infancy. As this infant universe expanded, it began to cool. Like a cosmic balloon inflating, the density decreased and the temperature dropped. For 380,000 years, this cooling continued while light remained trapped in the plasma, bouncing between electrons like pinballs in an endless arcade. Light filled the universe but could not travel freely. It was everywhere but invisible to any hypothetical observer. Then something extraordinary happened. When the universe cooled to about 3,000 degrees Kelvin, a critical threshold was crossed. For the first time, electrons could bind with protons to form neutral hydrogen atoms. This moment is known as recombination, though the name is somewhat misleading since these particles had never combined before. It was the first combination, not a recombination. With electrons now bound to atomic nuclei, photons suddenly found themselves in a transparent universe. Light, which had been continuously absorbed and re-emitted in the plasma, was now free to travel unimpeded across space. Imagine a foggy morning suddenly clearing, allowing sunlight to stream through in all directions. This light from the moment of recombination, this first free-streaming radiation, is what we now detect as the cosmic microwave background. It is quite literally the afterglow of creation, the oldest light in existence, a snapshot of the universe when it was just 380,000 years old, a mere infant in cosmic terms. But there's something strange about this ancient light. When it first began its journey, it was intensely hot, primarily in the visible and infrared parts of the spectrum. Yet today, we detect it not as visible light, but as microwaves. This is because the universe has continued expanding for 13.8 billion years, stretching those original light waves to about 1,000 times their original length. It's like listening to a song that has been progressively slowed down over billions of years. The original high notes have become deep bass tones. The original rainbow of visible light has become a bath of microwaves surrounding us from all directions. This cosmic microwave background, or CMB, was accidentally discovered in 1964 by Arno Penzias and Robert Wilson. They were radio astronomers working with a sensitive antenna at Bell Laboratories in New Jersey. While trying to detect radio waves from the Milky Way, they encountered a mysterious background noise, a faint hiss that seemed to come from everywhere in the sky with equal intensity. At first, they thought there must be something wrong with their equipment. They checked for interference, cleaned pigeon droppings from their antenna, and tried everything they could think of to eliminate this annoying noise. But the hiss persisted. It was constant, day and night, regardless of where they pointed their antenna. What they had stumbled upon, without initially realizing it, was the oldest light in the universe, the echo of the Big Bang itself. The cosmic microwave background had been predicted by cosmologists working on the Big Bang theory, but Penzias and Wilson knew nothing of these predictions. They had accidentally discovered one of the most important pieces of evidence for the Big Bang theory, a finding that would eventually earn them the Nobel Prize in Physics. Today, we've studied the cosmic microwave background in exquisite detail, using satellites like COBE, WMAP, and Planck. These observations reveal that while the CMB is remarkably uniform, it's not perfectly so. There are tiny temperature variations, differences of only about 1 part in 100,000. But these subtle fluctuations are immensely important. These minute differences represent the seeds of cosmic structure. The slightly denser regions in the early universe would eventually grow through gravity to become galaxies and galaxy clusters. The slightly less dense regions would become the cosmic voids. The entire large-scale structure of the modern universe, with its magnificent filaments of galaxies stretched across space like a cosmic web, was encoded in these tiny temperature variations in the primordial light. It's as though the cosmic microwave background is a baby picture of the universe, showing the earliest features that would grow to become the mature cosmic structures we see today. By studying these subtle patterns in the CMB, cosmologists can determine fundamental properties of the universe, including its age, composition, and geometry. One of the most remarkable findings from CMB studies is that our universe appears to be geometrically flat. In the same way that Earth appears flat locally, even though it's globally a sphere, our universe shows no curvature on the largest observable scales. This flatness requires an extraordinarily precise balance between the universe's expansion rate and its matter density, raising profound questions about why conditions after the Big Bang were so finely tuned. The cosmic microwave background also tells us about the composition of the universe. By analyzing its patterns, cosmologists have determined that ordinary matter, the kind that makes up stars, planets, and people, accounts for only about 5% of the universe's content. About 27% is dark matter, a mysterious substance that doesn't interact with light but exerts gravitational pull. The remaining 68% is dark energy, an even more enigmatic component that appears to be accelerating the universe's expansion. In essence, the CMB reveals that we live in a universe dominated by things we cannot see or directly detect, with ordinary matter being just a minor component of the cosmic inventory. We are, in a very real sense, the exception rather than the rule in the cosmos. This ancient whisper also contains clues about what happened in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. During this period, a theoretical process called inflation may have expanded the universe exponentially, stretching quantum fluctuations to cosmic scales. The patterns we see in the CMB are consistent with this inflationary model, giving us a window into physics at energy scales far beyond what any particle accelerator on Earth could ever achieve. The cosmic microwave background is truly democratic in its distribution. No matter where you are in the universe, you would detect this radiation coming from all directions. It forms a perfect sphere around any observer, with the radius of that sphere being the distance light has traveled since the moment of recombination, approximately 13.8 billion light-years. This means the CMB forms the boundary of our observable universe. We cannot see beyond it because light from greater distances hasn't had time to reach us yet. It's as though we live inside a cosmic snow globe, with the CMB forming the interior surface of the globe, the farthest reach of our cosmic vision. And yet, remarkably, this ancient radiation remains with us today. It permeates all of space, including the room where you are right now. About 1% of the static on an untuned analog television comes from the cosmic microwave background. When you see that snowstorm pattern on an old TV set, a small fraction of what you're seeing is actually the afterglow of the Big Bang itself, photons that have been traveling for 13.8 billion years only to end their epic journey by striking the electronics in your television. In this way, the beginning of the universe is not just a distant historical event, but a presence that surrounds us continuously. Every cubic centimeter of space contains about 411 photons from the cosmic microwave background. They fly through your body by the trillions every second, silent messengers from the dawn of time. If you could somehow see microwave radiation with your eyes, the entire sky would glow with a nearly uniform brightness, day and night. This glow would be extraordinarily cold, just 2.7 degrees above absolute zero on the Kelvin scale. But it would be everywhere, a constant reminder of our universe's fiery birth. The cosmic microwave background is more than just ancient light. It is the first echo in a universe full of echoes. It is the whisper of creation itself, still reverberating through space after nearly 14 billion years. And in its subtle patterns, we find the embryonic blueprint for everything that would follow, including the galaxies, stars, planets, and ultimately, observers like ourselves, who could one day decode its message. What happens when a star screams its final words into the void? Among all the whispers and echoes of the cosmos, some begin as violent shouts. Supernovae are the most energetic events in the modern universe. Explosions so powerful they can briefly outshine entire galaxies containing hundreds of billions of stars. Yet even these cosmic shouts eventually fade to whispers, leaving traces that persist for millions of years. Imagine a star much more massive than our Sun, perhaps 20 or 30 times larger. Throughout its life, this giant has been fighting a constant battle between gravity pulling inward and the pressure of nuclear fusion pushing outward. For millions of years, this delicate balance remains stable. The star shines brightly, fusing hydrogen into helium in its core, just as our Sun does. But massive stars burn through their fuel far more quickly than stars like our Sun. When the hydrogen in the core is exhausted, the star begins fusing helium into carbon. When the helium runs out, carbon fuses into oxygen, then neon, then silicon. Each transition happens more rapidly than the last. What took millions of years in the beginning now takes just days or hours. The star becomes like an onion, with layers of progressively heavier elements surrounding a core of iron. And here lies the trap. Iron is nuclear fusion's dead end. Fusing iron atoms doesn't release energy, it consumes it. With fusion no longer generating the outward pressure needed to counteract gravity, the star faces catastrophe. The iron core collapses, falling inward at about 23% the speed of light. The collapse happens in less than a second. The core shrinks from roughly the size of Earth to a ball of neutrons just 10 miles across. This neutron core is so dense that a teaspoonful would weigh about 1 billion tons. The material falling onto this newly formed neutron core bounces, creating a shock wave that tears through the outer layers of the star. Meanwhile, a flood of neutrinos, ghostly particles that rarely interact with matter, streams outward from the collapsing core. These neutrinos carry away about 99% of the supernova's energy. The remaining 1% powers the visible explosion we can see across billions of light years. The result is astounding. For a brief time, typically about 2 weeks, a single dying star can outshine 10 billion suns. If a supernova happened within 50 light years of Earth, it would appear brighter than the full moon, visible even in daylight. Fortunately for us, no such stars exist close enough to pose this danger. These stellar explosions are cosmic forges, creating most of the elements heavier than iron in the periodic table. Gold, silver, platinum, uranium, all were synthesized in the extreme conditions of supernovae. The atoms in your gold jewelry, the uranium powering nuclear plants, even the iodine in your thyroid gland were all created in the final moments of dying stars. As Carl Sagan famously noted, "We are literally made of star stuff." But what happens after the brilliant flash fades? This is where the shout becomes a whisper, an echo that continues to reverberate through space long after the initial explosion. The material ejected from the supernova, traveling at thousands of kilometers per second, plows into the surrounding interstellar medium. This creates a supernova remnant, a complex structure of hot gas and dust that can persist for tens of thousands of years. These remnants are cosmic time capsules, preserving the memory of stellar deaths long after their light has faded from view. The Crab Nebula, located about 6,500 light-years from Earth in the constellation Taurus, is perhaps the most famous supernova remnant. It formed from a supernova so bright that it was visible in daylight for 23 days in the year 1054 CE. Chinese, Japanese, and Arab astronomers recorded this guest star that appeared suddenly in the sky, not realizing they were witnessing the death throes of a massive star. Today, nearly 1,000 years later, the Crab Nebula spans about 10 light-years across, still expanding at about 1,500 kilometers per second. At its center lies a pulsar, the rapidly rotating neutron star left behind by the explosion, spinning 30 times each second like a cosmic lighthouse. Each rotation sweeps beams of radiation through space, producing regular pulses when observed from Earth. The gas within the Crab Nebula still glows, energized by the pulsar and by the shock waves still moving through the material. It shines across the electromagnetic spectrum, from radio waves to gamma rays, each wavelength revealing different aspects of this ancient explosion. What began as one of the brightest events in recorded human history has become a beautiful, intricate nebula, a whisper of what was once a shout. The Veil Nebula in the constellation Cygnus offers an even older echo. This delicate network of glowing filaments is what remains of a star that exploded between 10,000 and 20,000 years ago. Spanning about 110 light-years, it continues to expand, its tendrils of gas still energized by the ancient explosion. The complex structures we see today reflect both the violence of the original explosion and the uneven distribution of the interstellar medium that it encountered during its expansion. Supernova remnants like these are not just beautiful celestial objects. They play a crucial role in galactic evolution. The shock waves from supernovae compress nearby clouds of gas and dust, potentially triggering the formation of new stars. This is cosmic recycling at its grandest scale. The death of one generation of stars seeds the birth of the next, an endless cycle of destruction and creation. The elements forged in supernovae also enrich the interstellar medium. Early generations of stars contained almost exclusively hydrogen and helium, the elements created in the Big Bang. But each successive generation incorporates more of the heavier elements expelled by supernovae, leading to more complex chemistry and, eventually, the possibility of planets like Earth and life forms like us. Some supernova remnants continue to evolve in surprising ways, producing cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. These particles, primarily protons and atomic nuclei, are accelerated by the magnetic fields associated with supernova remnant. When they eventually strike Earth's atmosphere, they create cascades of secondary particles that scientists detect using specialized observatories. Cosmic rays represent yet another way that ancient stellar explosions continue to influence our environment today. Some of these particles have been traveling through the galaxy for millions of years, preserving the memory of explosions long faded from view. They are literally the echoes of dead stars passing through our bodies at this very moment. Perhaps the most profound echo of supernovae is found in our own existence. Every atom of calcium in your bones, every atom of oxygen you breathe, was created inside a star and scattered by a supernova. We are walking collections of atoms forged in stellar furnaces and distributed through space by these cosmic explosions. Our bodies are made of recycled stardust, echoes of ancient stellar deaths. Even the iron in your blood, carrying oxygen to your cells, was created in the hearts of massive stars before they exploded. The phosphorus in your DNA, the potassium that allows your heart to beat, the zinc that strengthens your immune system, all were once part of stars that lived and died before our sun was born. In this sense, supernovae may shout briefly, but their whispers are eternal. They echo through the chemistry of planets, through the bodies of living things, through the ongoing cycle of stellar birth and death that characterizes our galaxy. Long after their visible light has faded, their influence continues in the elements they created and distributed throughout space. And occasionally, we catch glimpses of these echoes in real time. In February 1987, astronomers observed a supernova in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years from Earth. Known as supernova 1987A, it was the closest observed supernova since the invention of the telescope, providing an unprecedented opportunity to study these cosmic explosions. In the decades since, astronomers have watched as the shock wave from this explosion collides with rings of gas ejected by the star before it exploded. These collisions cause the rings to glow, creating an evolving display that continues to this day. The light from these collisions is literally an echo of the original explosion, reflected by the surrounding material and reaching us years after the initial flash. Similar light echoes have been detected from other historical supernovae. By observing light reflected off interstellar dust clouds, astronomers have been able to study supernovae that occurred hundreds of years ago, long before modern telescopes existed. These reflected rays allow us to analyze explosions from multiple angles and at different times, providing insights that would be impossible from direct observation alone. Supernovae, then, are not merely momentary events, but ongoing processes whose effects ripple through space and time. They begin as brief, spectacular shouts that shake their host galaxies, but they transform into whispers that persist for eons, echoing through the cosmos in forms ranging from expanding shells of gas to the elements in our bodies. In a universe full of echoes, these stellar explosions produce some of the most profound and far-reaching reverberations. Their light may fade, but their influence continues, shaping the evolution of galaxies and making possible the existence of complex chemistry, planets, and ultimately, life itself. What happens when space itself ripples like water? For most of human history, we've relied on light to understand the universe. But there's another kind of echo traveling through the cosmos, one that doesn't require any medium, one that passes through solid matter as though it weren't there. These are gravitational waves, ripples in the fabric of space-time itself, carrying information about the most violent events in the universe. To understand gravitational waves, we must first understand how Einstein revolutionized our concept of gravity. In his general theory of relativity, published in 1915, Einstein proposed that gravity isn't a force as Newton had suggested, but rather the result of massive objects warping the fabric of space-time. Imagine placing a bowling ball on a trampoline. The ball creates a depression, and smaller objects like marbles will naturally roll toward it. They follow the curvature of the trampoline surface, not because the bowling ball is pulling them directly, but because they're following the path of least resistance through curved space. In Einstein's view, planets orbit the sun not because the sun pulls on them, but because the sun's mass curves the space-time around it, creating a gravitational well that planets follow as they move through space. This revolutionary idea transformed our understanding of gravity and made a bold prediction. If mass curves space-time, then moving masses should create ripples in this cosmic fabric, much as a boat creates waves as it moves through water. These ripples, or gravitational waves, travel at the speed of light, carrying energy and information away from their source. But they are extraordinarily subtle. Even the most powerful gravitational waves would change the distance between Earth and the Moon by less than the width of an atom. Detecting such minute distortions in space-time seemed impossible when Einstein first predicted them. For decades, gravitational waves remained a theoretical curiosity, mathematically elegant, but beyond our ability to observe directly. Some physicists even questioned whether they existed at all. Einstein himself vacillated on the question, at times doubting his own predictions. The challenge was immense. How do you detect distortions in space-time smaller than a proton? The answer came in the form of laser interferometry. Imagine two perfectly straight rulers laid perpendicular to each other, forming an L shape. Now imagine measuring the lengths of these rulers with extraordinary precision, using laser light to detect any changes. If a gravitational wave passes through, one ruler will momentarily stretch while the other contracts, then vice versa, as the wave oscillates through space. By measuring these minute changes in length, scientists could potentially detect gravitational waves passing through Earth. This concept led to the construction of the Laser Interferometer Gravitational Wave Observatory, or LIGO. With facilities in Hanford, Washington, and Livingston, Louisiana, LIGO consists of two L-shaped detectors, each with arms 4 kilometers long. Inside these arms, laser beams bounce back and forth between mirrors, precisely measuring any changes in the arm's lengths. The sensitivity required is almost beyond comprehension. LIGO can detect changes in length of less than 1/10,000th the width of a proton. This is equivalent to measuring the distance to the nearest star with an accuracy of less than the width of a human hair. To achieve this sensitivity, LIGO must eliminate all other sources of vibration, from passing trucks to distant earthquakes, even the thermal motion of atoms in the mirrors themselves. After decades of development and refinement, LIGO finally achieved the necessary sensitivity, and on September 14, 2015, both detectors captured a signal that would change astronomy forever. The distinctive chirp, rising in both frequency and amplitude before suddenly stopping, matched exactly what theoretical physicists had predicted for the merger of two black holes. Analysis revealed that 1.3 billion years ago, two black holes, with masses of 36 and 29 times that of our Sun, spiraled together and merged into a single black hole. In the final fraction of a second, they released energy equivalent to 3 solar masses, all converted to gravitational waves, according to Einstein's famous equation, E equals mc squared. This energy, in the form of space-time ripples, traveled across more than 1 billion light-years before passing through Earth, momentarily stretching and compressing our planet by a tiny fraction. The detection of gravitational waves confirmed one of the last major predictions of Einstein's general relativity, but more importantly, it opened an entirely new way of observing the universe. If traditional astronomy is like seeing the cosmos, gravitational wave astronomy is like hearing it. Each provides different information, revealing aspects of the universe that would remain hidden if we relied on just one sense. Since that first detection, dozens more gravitational wave events have been observed. Most involve the mergers of black holes or neutron stars, the densest objects in the universe. Each detection allows astronomers to calculate the masses of these objects, their spins, and how far away they are, even when they emit no detectable light. Perhaps the most spectacular gravitational wave detection came on August 17, 2017. On that date, LIGO detected waves from the merger of two neutron stars, objects with masses slightly greater than our Sun, but compressed into spheres just 10 miles across. Unlike black hole mergers, which are generally invisible to electromagnetic telescopes, neutron star mergers produce light across the spectrum, from gamma rays to radio waves. Within seconds of the gravitational wave detection, NASA's Fermi satellite detected a gamma-ray burst from the same region of sky. This triggered a worldwide observing campaign, with telescopes across the globe turning to watch the aftermath of this cosmic collision. The resulting observations confirmed several long-standing theories, including the idea that neutron star mergers are responsible for creating most of the gold, platinum, and other heavy elements in the universe. This event, dubbed GW170817, marked the beginning of multi-messenger astronomy, where the same cosmic event is observed through different astronomical messengers, gravitational waves, and light. It's like both seeing and hearing a thunderstorm, with each sense providing different but complementary information. But what makes gravitational waves particularly special as cosmic echoes is their ability to travel unimpeded through matter. Light can be absorbed, scattered, or blocked by gas and dust, limiting how far back in time we can see with traditional telescopes. Gravitational waves, however, pass through everything. A gravitational wave created at the beginning of the universe could theoretically reach us today, carrying information about cosmic processes that predate the cosmic microwave background. This ability to penetrate matter also means gravitational waves carry information from regions that are otherwise invisible. The interiors of supernovae, the regions around black hole horizons, the earliest moments after the Big Bang, all produce gravitational radiation that can reach our detectors without being altered by intervening matter. Consider what happens during a supernova explosion. The light produced might take hours or days to escape from the outer layers of the dying star, and what we see has been processed and modified by its journey. But gravitational waves generated by the collapsing core would escape immediately, reaching us before the first photons and carrying pristine information about the collapse itself. Gravitational waves also preserve more information than light about their sources. From a gravitational wave signal, astronomers can determine the masses of the merging objects, their spins, their orientations, and even test whether gravity behaves, as Einstein predicted in these extreme environments. Each gravitational wave signal is a treasure trove of data, allowing tests of fundamental physics impossible with electromagnetic observations alone. And unlike light, which exists in a pre-existing universe, gravitational waves are literally ripples in space-time itself. They don't travel through the universe so much as they are waves in the universe. This makes them the most fundamental of all cosmic messengers, echoes not of matter or energy, but of space and time themselves. The waves we've detected so far are just the beginning. Future observatories, both on Earth and in space, will detect gravitational waves from a wider range of sources. The European Space Agency is developing the Laser Interferometer Space Antenna, or LISA, which will use 3 spacecraft separated by millions of kilometers to detect lower frequency gravitational waves than LIGO can measure. This will open new windows into the cosmos, allowing us to observe the mergers of supermassive black holes at the centers of galaxies and potentially detect the background hum of countless smaller gravitational wave sources throughout the universe. Perhaps most exciting is the possibility of detecting primordial gravitational waves, ripples created in the first instance after the Big Bang. These waves could provide our only direct window into cosmic inflation, the theorized period of exponential expansion that occurred just 10 to the negative 36 seconds after the universe began. Detecting these primordial gravitational waves would not only confirm inflation, but also provide details about physics at energy scales far beyond what particle accelerators on Earth can achieve. In some ways, gravitational waves are the most permanent echoes in our universe. While light can be absorbed or scattered, gravitational waves continue their journey largely unchanged. The ripples from ancient black hole mergers, from the births and deaths of the first stars, from the earliest moments of the universe itself, all continue to propagate through the cosmos. They carry information across billions of light years and billions of years, silent witnesses to events long forgotten by the rest of the universe. And remarkably, these waves are passing through you right now. Countless gravitational ripples from across the universe are stretching and compressing your body by infinitesimal amounts as you listen to these words. You don't feel them, of course. The changes are far too small to detect without instruments of extraordinary sensitivity. But they are there, a constant cosmic massage from the most energetic events in the universe's history. When a star dies in a supernova, when black holes collide in distant galaxies, when neutron stars smash together in cosmic cataclysms, they don't just shine brightly for a moment before fading away. They leave behind these subtle ripples in space-time, echoes that will continue traveling outward forever, carrying the story of their creation to the farthest reaches of the cosmos. In a universe defined by impermanence, Where stars burn out and galaxies fade away, gravitational waves offer a kind of permanence. Once created, they simply continue, their energy spreading out but never disappearing entirely. They are the universe's longest-lasting echoes, cosmic whispers that may outlive stars, galaxies, and perhaps even black holes themselves. So when we detect a gravitational wave, we aren't just observing a distant event. We're connecting with a cosmic echo that has traveled across unimaginable distances, carrying the imprint of cataclysms that occurred before Earth, before our sun, perhaps before our galaxy existed. We are listening to the silent vibrations of the cosmos itself, hearing the universe as it speaks in its most fundamental voice. And what we've heard so far is just the beginning. As our detectors improve, as new observatories come online, we will detect fainter signals from more distant sources. The universe's gravitational wave symphony is rich and complex, with each type of cosmic event producing its own distinctive pattern of space-time ripples. We have only begun to understand this cosmic music, to distinguish its instruments and melodies. Like all great scientific advances, gravitational wave astronomy doesn't just answer existing questions. It raises new ones. Did primordial black holes exist in the early universe? Can gravitational waves tell us whether Einstein's theory of gravity is complete, or whether it requires modification? The answers to these questions and many more lie encoded in the gravitational waves, still traveling toward Earth from across the cosmos. In a very real sense, gravitational waves represent the universe talking to itself. The mass and energy in one region of space-time sends ripples outward that influence distant regions. Information about cosmic events propagates at the speed of light, connecting disparate parts of the universe in a vast web of cause and effect. We are merely eavesdroppers on this cosmic conversation, using our ingenuity to detect and decode messages never intended for human ears. And yet, in detecting these waves, in translating their subtle language into something we can understand, we participate in one of the most profound acts of cosmic connection possible. We reach across billions of light years and billions of years to touch events that shaped our universe. We become part of this vast web of cosmic echoes, not just passive listeners, but active interpreters of the universe's ongoing story. Have you ever turned on an old radio, spinning the dial between stations, and heard strange whistles, pops, and hisses emanating from the speakers? Some of that static isn't interference from earthly sources. It's the voice of the cosmos itself. The universe is filled with radio waves, invisible to our eyes but detectable with the right instruments. These waves are among the most persistent echoes in the cosmos, carrying information across vast distances and revealing phenomena invisible to optical telescopes. Unlike the visible light our eyes can detect, radio waves have much longer wavelengths, ranging from millimeters to kilometers. This gives them a remarkable ability to penetrate dust clouds, travel through the ionized gas that permeates much of space, and reach us from the most distant corners of the observable universe. In many ways, radio waves are the ultimate cosmic whispers, subtle signals that can travel where visible light cannot go. The story of radio astronomy begins in the 1930s, when an engineer named Karl Jansky was investigating sources of static that might interfere with transatlantic telephone calls. Using a rotating antenna nicknamed Jansky's merry-go-round, he detected a persistent hiss that peaked every 23 hours and 56 minutes, the time it takes Earth to complete one rotation relative to the distant stars. Jansky had discovered radio waves coming from the center of the Milky Way galaxy, opening an entirely new window on the cosmos. But it was during World War II that radio astronomy truly blossomed. Radar operators noticed interference that appeared at the same time each day. After eliminating all possible terrestrial sources, they realized they were detecting radio emissions from the sun. When the war ended, many radar engineers turned their expertise toward astronomy, building larger and more sensitive antennas to detect fainter cosmic radio sources. What they discovered transformed our understanding of the universe. radio telescopes revealed objects and phenomena completely invisible to optical instruments. Among the most fascinating were pulsars, rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As these stars spin, the beams sweep across space like cosmic lighthouses, producing regular pulses when they cross Earth's location. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University. She noticed unusual regular pulses in the data from a radio telescope she had helped build. These pulses came every 1.337 seconds with such precision that Bell and her supervisor, Anthony Hewish, briefly considered whether they might be signals from an extraterrestrial civilization. They whimsically labeled the source LGM-1 for Little Green Men. Further investigation revealed a natural explanation even more extraordinary than aliens. Pulsars are the remnants of massive stars that have exploded as supernovae, leaving behind cores so dense that electrons and protons combine to form neutrons. These neutron stars contain about 1.4 times the mass of our Sun, compressed into a sphere just 20 kilometers in diameter. A teaspoonful of neutron star material would weigh billions of tons on Earth. These stellar remnants rotate rapidly, often dozens or hundreds of times per second. The fastest known pulsar, PSR J1748-2446 AD, spins at 716 times per second, its surface moving at about 24% the speed of light. Despite these incredible speeds, pulsars maintain astonishingly precise timing, with some keeping time better than the most accurate atomic clocks on Earth. This precision makes pulsars valuable cosmic tools. By monitoring slight changes in their pulse arrival times, astronomers have confirmed the existence of gravitational waves, measured the masses of planets in our solar system, and even created a galactic GPS system that could someday guide spacecraft through the Milky Way. But pulsars do more than keep time. They fill the galaxy with radio waves that continue long after the pulsar itself may have faded from view. The radio signals from the oldest pulsars have been traveling through space for millions or even billions of years, creating expanding shells of radiation that wash over planets and stars throughout the Milky Way. These signals are so persistent that they might serve as beacons for distant civilizations. While the signals weaken with distance, they remain detectable with sufficiently sensitive equipment. Indeed, the first detection of a pulsar by humans was a mere cosmic eye blink ago, in astronomical terms. How many other civilizations might have detected these same signals over the millions of years they've been traveling through space? But pulsars aren't the only cosmic radio sources. Perhaps even more enigmatic are fast radio bursts, or FRBs. First discovered in 2007, these intense flashes of radio waves last just milliseconds, but can release more energy in that brief moment than our Sun produces in decades. The origins of these mysterious bursts remained unknown for years, with theories ranging from evaporating black holes to advanced alien civilizations. Recent observations suggest that at least some FRBs come from magnetars, neutron stars with extremely powerful magnetic fields. When the magnetic field of a magnetar rearranges itself, it can release an enormous burst of energy, part of which emerges as radio waves. These bursts can be detected billions of light years away, making them among the most luminous radio sources in the universe. What makes FRBs particularly interesting as cosmic echoes is that they allow astronomers to probe the material between Earth and their sources. As radio waves travel through space, they encounter free electrons in the interstellar and intergalactic medium. These encounters cause different frequencies within the burst to travel at slightly different speeds, with lower frequencies arriving later than higher ones, a phenomenon called dispersion. By measuring this dispersion, astronomers can estimate how much matter the signal passed through on its journey to Earth. This provides a unique way to measure the density of the intergalactic medium, the tenuous gas that fills the vast spaces between galaxies. In essence, FRBs serve as cosmic flashlights, illuminating material that would otherwise remain invisible. Some FRBs appear to repeat, sending multiple bursts from the same location over time. The first repeating FRB, known as FRB 12102, has emitted hundreds of bursts since its discovery. By monitoring these repetitions, astronomers hope to better understand the mechanisms that produce these enigmatic signals, and perhaps use them as tools to study the structure of the universe on the largest scale. Radio waves also reveal the presence of vast clouds of hydrogen gas, the most abundant element in the universe and the primary material from which stars form. Hydrogen atoms emit radio waves with a characteristic wavelength of 21 centimeters when their electrons change spin states. This emission, known as the hydrogen line, allows astronomers to map the distribution of gas in our galaxy and in distant galaxies, even when this gas is too cold and diffused to be detected by other means. These hydrogen maps reveal the spiral structure of galaxies, track the rotation of galactic disks, and show the flows of gas being pulled into or expelled from galaxies. They are among the most important tools for understanding galaxy formation and evolution, providing information that would be completely hidden in optical observations. Radio observations also reveal the presence of enormous jets of material blasting out from the centers of active galaxies. These jets, which can extend for millions of light years, are produced when matter falls into the supermassive black holes at galactic centers. The extreme conditions near these black holes accelerate particles to nearly the speed of light and generate intense magnetic fields that collimate the outflow into narrow beams. These relativistic jets emit strongly in radio wavelengths through a process called synchrotron radiation, produced when charged particles spiral around magnetic field lines. The radio emission from these jets can persist for millions or even billions of years, creating vast lobes of radio-emitting plasma that can dwarf the visible galaxy itself. One of the most spectacular examples is Centaurus A, a nearby galaxy with radio lobes extending 1.5 million light-years from the central black hole. If our eyes could see radio waves, these lobes would appear 8 times larger than the full moon in our sky, despite being 12 million light-years away. These enormous structures are cosmic echo chambers, where the energy from a feeding black hole reverberates long after the active phase has ended. Radio waves also reveal the presence of cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. When these particles interact with galactic magnetic fields, they emit synchrotron radiation primarily in radio wavelengths. This creates a diffuse radio glow throughout the galaxy, a whisper of the cosmic rays that fill our Milky Way. These cosmic rays are themselves echoes of violent events. Many are produced in supernova remnants, where the shock waves accelerate particles to extreme energies. Others may come from active galactic nuclei or other powerful cosmic accelerators. Once accelerated, cosmic rays can travel for millions of years through the galaxy, their paths twisted by magnetic fields into complex spirals. When they finally decay or interact with other matter, they produce the radio whispers we detect with our telescopes. The discovery of the cosmic microwave background, which we discussed in Chapter 2, was also made through radio astronomy. This most ancient light in the universe now appears as microwave radiation, a form of radio waves. Its discovery by Penzias and Wilson in 1964 using a radio antenna designed for satellite communications demonstrates how the universe's oldest echo was detected not through massive optical telescopes, but through radio receivers tuned to the cosmos. Radio waves even allow us to listen to the planets in our solar system. Jupiter is particularly noisy in radio wavelengths, emitting bursts of radiation produced by its intense magnetic field interacting with particles from its volcanic moon Io. These emissions, known as Jupiter's decometric radiation, can be detected with relatively simple equipment. Amateur radio astronomers around the world regularly listen to Jupiter's radio voice, an ever-changing chorus of whistles, bursts, and static. Saturn, too, produces radio emissions, particularly from auroras near its poles. These signals, known as Saturn kilometric radiation, were studied extensively by the Cassini spacecraft during its 13-year mission orbiting the ringed planet. Even our own Earth generates radio signals, particularly during auroral activity, when charged particles from the Sun interact with our magnetic field. What makes radio waves particularly special as cosmic echoes is their longevity. Unlike visible light, which can be easily absorbed by dust, radio waves can travel enormous distances through the interstellar medium, with relatively little attenuation. This means that radio signals from ancient cosmic events can reach us even when all other forms of electromagnetic radiation have been blocked or absorbed. Consider, for example, the center of our own Milky Way galaxy. In visible light, the galactic center is completely obscured by thick clouds of dust that absorb optical wavelengths. But radio waves pass through these dust clouds relatively unimpeded, revealing the complex structure of gas clouds, star clusters, and the supermassive black hole at the heart of our galaxy. Radio waves also have a unique relationship with water, another crucial cosmic ingredient. Water molecules produce natural laser-like emissions called masers when they are excited by energy from nearby stars or other sources. These water masers produce intense radio signals at specific frequencies, allowing astronomers to detect water in distant galaxies and track the motions of gas clouds with extraordinary precision. By measuring the Doppler shifts of these water masers, astronomers have been able to create detailed maps of the material orbiting the supermassive black holes at the centers of some galaxies. These observations provide some of the strongest evidence for the existence of these black holes and allow precise measurements of their masses. Radio waves can also tell us about the magnetic fields that permeate the cosmos. When radio waves pass through a region with a magnetic field, their polarization is rotated, an effect known as Faraday rotation. By measuring this rotation, astronomers can map the strength and direction of magnetic fields in our galaxy and beyond, revealing another invisible component of the cosmic ecosystem. These magnetic fields are themselves echoes of ancient processes. They may have originated in the early universe, been amplified by the first generation of stars, or been generated by dynamo processes in the turbulent gas of forming galaxies. However they arose, they now thread through the cosmic web, influencing the flow of gas, the formation of stars, and the propagation of cosmic rays. Perhaps most intriguingly, radio waves might someday bring us echoes from other technological civilizations. The search for extraterrestrial intelligence, or SETI, primarily uses radio telescopes to search for artificial signals from beyond Earth. The logic is compelling. Radio waves travel at the speed of light, suffer minimal absorption by interstellar gas and dust, and can be generated with relatively modest energy requirements. If another civilization wanted to announce its presence to the cosmos, radio waves would be an excellent choice of messenger. Our own civilization has been broadcasting radio signals for just over a century, creating an expanding bubble of radio emissions now about 100 light-years in radius. Any civilizations within this bubble, with sufficiently sensitive radio telescopes, could potentially detect evidence of our technological society. Similarly, we might someday detect the radio leakage or deliberate transmissions from other civilizations, bringing us echoes not just of natural cosmic processes, but of alien thoughts and cultures. Whether or not we ever detect signals from extraterrestrial intelligence, radio astronomy will continue to reveal aspects of the universe invisible to other forms of observation. These long-wavelength whispers carry information across vast distances and timescales, connecting us to events that happened millions or billions of years ago in distant corners of the cosmos. In a universe filled with echoes, radio waves are among the most persistent and revealing. They penetrate dust clouds, traverse intergalactic voids, and bring us news of cosmic events long after they've faded from view in other wavelengths. They reveal the invisible scaffolding of gas and magnetic fields that shapes visible structures. They connect us to the most violent and energetic phenomena in the universe, from feeding black holes to colliding neutron stars. And perhaps most poetically, some of the radio waves we detect today from distant cosmic sources began their journey before life existed on Earth. They've traveled for billions of years across the expanding cosmos, only to end their epic voyage in the sensitive receivers of our radio telescopes, bringing us messages from a universe that existed long before we were here to listen. What if entire galaxies could fade from view, becoming invisible to all but the most sensitive instrument? Throughout the cosmos, there exist shadow realms, collections of stars and gas so diffuse and dim that they evaded detection for decades, despite containing billions of solar masses of material. These are ghost galaxies, the after-images of cosmic structure, whispering reminders that much of the universe remains hidden from our sight. When you picture a galaxy, you likely imagine something magnificent and obvious, like the Andromeda Galaxy with its luminous spiral arms, or perhaps an elliptical galaxy glowing with the light of hundreds of billions of stars. These cosmic metropolises dominate astronomical catalogues because they're easy to see, their brilliance announcing their presence across vast distances. But what if many, perhaps most, galaxies don't announce themselves so boldly? The first hints of these ghost galaxies came in the 1960s and 1970s, when astronomers surveying the skies for dwarf galaxies orbiting the Milky Way kept finding fewer than theoretical models predicted. This became known as the missing satellites problem. According to simulations of galaxy formation based on the standard cosmological model, our galaxy should be surrounded by hundreds or even thousands of smaller satellite galaxies. Yet only a dozen or so were known. Where were the rest? The answer began to emerge in 2005, when the Sloan Digital Sky Survey, a project that mapped a quarter of the night sky in unprecedented detail, revealed something astonishing. Hidden among the stars of our galaxy were incredibly faint dwarf galaxies that had gone unnoticed because they were so diffuse and dim. The first of these, called Ursa Major I, contains about 100,000 stars spread across an area, nearly the size of the full moon in our sky. Yet its total light output is less than that of a single bright, giant star. Since then, dozens more of these ultra-faint dwarf galaxies have been discovered, each containing thousands to millions of stars. They have poetic names like Bootes I, Hercules, and Segway 1, often named after the constellations in which they were found. Segway 1, discovered in 2006, is one of the least luminous galaxies known, with a luminosity just 300 times that of our Sun despite containing hundreds of thousands of stars. What makes these ghost galaxies so elusive is not just their faintness, but their extraordinary diffuseness. The stars within them are spread so thinly that they barely stand out against the background. Imagine walking through a forest where the trees are spaced kilometers apart. From outside, you might not recognize it as a forest at all, just a landscape with occasional trees. Similarly, these ultra-faint galaxies have stars separated by such vast distances that they appeared to be merely random field stars until careful statistical analysis revealed their association. But ghost galaxies aren't just curiosities. They may be the most common type of galaxy in the universe. For every bright spiral galaxy like the Milky Way, there may be dozens or hundreds of these dim, diffuse systems lurking just at or below the threshold of detection. They represent a shadow universe, a population of galaxies that have existed alongside their brighter cousins since the early days of the cosmos, but remained hidden from view due to our technological limitations. Even more intriguing is what these ghost galaxies tell us about dark matter, the invisible substance that makes up about 85% of the matter in the universe. When astronomers measure the motion of stars in these ultra-faint galaxies, they find something remarkable. The stars are moving much faster than can be explained by the gravitational pull of the visible matter alone. In fact, some of these dwarf galaxies are among the most dark matter-dominated objects known, with dark matter outweighing normal matter by factors of hundreds or even thousands. Segue 1, for instance, has about 600 solar masses of visible stars, but exists within a dark matter halo containing about 600,000 solar masses. That's 1,000 times more dark matter than normal matter, making it an almost pure dark matter laboratory floating through space. By studying the motions of its handful of visible stars, astronomers can probe the properties of the dark matter halo in which they're embedded, gaining insights into the nature of this mysterious substance. These ghost galaxies challenge our understanding of galaxy formation and evolution. In the Standard Model, galaxies form when gas cools and condenses within halos of dark matter, eventually forming stars. But in these ultra-faint dwarfs, this process seems to have been extraordinarily inefficient. Something prevented them from forming stars with the same vigor as their brighter counterparts. Perhaps the first generation of stars created winds that blew away the remaining gas, or perhaps the ultraviolet radiation from these early stars ionized the gas and prevented it from cooling and forming more stars. Some ghost galaxies might be the remnants of once brighter systems that have been slowly torn apart by the gravitational pull of larger galaxies like the Milky Way. As a small galaxy orbits a larger one, the tidal forces can strip away its outer stars, creating long streams that eventually dissolve into the larger galaxy's halo. Before disappearing completely, these disrupted systems pass through a ghost phase, where they're barely detectable as coherent structures. The Sagittarius dwarf galaxy, discovered in 1994, exemplifies this process. Located about 70,000 light-years from Earth, it is currently being torn apart by the Milky Way's gravitational pull. Long streams of stars from this disrupted galaxy now wrap around our entire galaxy, forming multiple loops like a cosmic snake. Eventually, all its stars will be assimilated into the Milky Way's halo, and the Sagittarius dwarf will cease to exist as a distinct entity. But for now, it lingers as a ghost, a fading echo of a once independent galaxy. Astronomers have detected similar streams from other disrupted dwarf galaxies, creating a complex network of stellar rivers flowing through our galaxy's halo. Each stream is a fossil record of a galactic merger, an echo of a structure that once existed independently but is now being incorporated into our galaxy. By mapping these streams, astronomers can reconstruct the Milky Way's history of galactic cannibalism, determining how many smaller galaxies it has consumed over its lifetime. But ghost galaxies aren't limited to the dwarf satellites orbiting larger galaxies. In recent years, astronomers have discovered an entirely different class of ghostly systems lurking in the space between galaxy clusters. These are the ultra-diffuse galaxies, systems as large as the Milky Way in physical extent, but containing only about 1% as many stars. The first examples were found in the Coma Cluster, a dense collection of thousands of galaxies, about 330 million light-years from Earth. These ultra-diffuse galaxies have diameters of 30 to 60,000 light-years, similar to the Milky Way, but are so diffuse that their central regions are nearly as dark as the night sky. They contain old, reddish stars with little evidence of ongoing star formation, suggesting they are ancient systems that formed their stars long ago and have been slowly fading ever since. How these strange galaxies formed remains a mystery. One possibility is that they began as normal galaxies, but had most of their gas stripped away when they fell into the galaxy cluster, preventing the formation of new stars. Another theory suggests they are failed galaxies, systems where star formation was truncated early, perhaps due to powerful outflows from their first generation of stars. A third possibility is that they formed with unusual initial conditions, starting with more widely distributed gas than typical galaxies. Whatever their origins, these ultra-diffuse galaxies are challenging to study precisely because they're so faint. Their surface brightness is less than 1% that of the night sky, making them nearly invisible even to powerful telescopes unless observed with special techniques. They were discovered only recently because astronomical surveys have become sensitive enough to detect such diffuse objects. This raises the question of how many other ghost galaxies might still lurk undiscovered in the darkness between the brighter systems that dominate our cosmic map. Some ultra-diffuse galaxies hold additional surprises. In 2018, astronomers studying an ultra-diffuse galaxy called NGC 1052-DF2 made a shocking discovery. Unlike most galaxies, which contain more dark matter than normal matter, DF2 appeared to have little or no dark matter at all. Its stars moved at speeds consistent with the gravitational pull of the visible matter alone, without the need for an invisible component. This challenged the standard understanding that dark matter is necessary for galaxy formation, suggesting that at least some galaxies can form through alternative processes. A year later, a second dark matter-deficient ultra-diffuse galaxy was found, NGC 1052-DF4, with similar properties to DF2. Both exist near a massive elliptical galaxy, suggesting their unusual properties might be the result of interactions with this larger neighbor. Perhaps they are the remnants of more massive galaxies that were stripped of both their dark matter and their outer stars, leaving behind only their central regions as ghostly reminders of their former existence. Not all ghost galaxies are ancient systems in decline. Some are actually quite young but remain difficult to detect because they haven't yet formed many stars. These systems, known as dark galaxies, consist primarily of atomic and molecular hydrogen gas with very few stars. They're nearly invisible in optical wavelengths, but can be detected through their emission or absorption of radio waves. One candidate dark galaxy, Smith's Cloud, is currently on a collision course with the Milky Way. Discovered in 1963 by astronomer Gail Smith, this massive cloud of hydrogen contains enough material to form about 1 million stars the size of our Sun. Yet despite its enormous mass, it contains no detectable stars. Currently located about 40,000 light-years from the Milky Way's disk, it's expected to collide with our galaxy in about 30 million years, potentially triggering a burst of star formation in the impact region. Smith's Cloud raises intriguing questions. Is it a pristine cloud of gas that never formed stars? Or is it the stripped remains of a once normal galaxy that lost its stars through interactions with the Milky Way? Recent measurements suggest it contains elements heavier than hydrogen and helium, indicating that at least some of its material has been processed through stars at some point in its history. Perhaps it is not a true dark galaxy, but rather the ghostly remnant of a once bright system. The existence of these various types of ghost galaxies, from ultra-faint dwarfs to ultra-diffuse giants to dark galaxies rich in gas but poor in stars, suggests that the universe is far more diverse and complex than our traditional galaxy classifications indicate. For decades, astronomers classified galaxies primarily by their visual appearance, sorting them into spirals, ellipticals, and irregulars. But ghost galaxies hint at a shadow taxonomy, a classification of systems that barely register in optical surveys but nonetheless contribute significantly to the cosmic inventory. Perhaps the most profound implication of ghost galaxies is what they tell us about the universe's bookkeeping. If these nearly invisible systems are as common as some estimates suggest, then a significant fraction of the universe's normal matter might be locked up in systems that are difficult or impossible to detect with current technology. This missing matter would join the other cosmic fugitives, dark matter and dark energy, in the category of cosmic components that influence the universe's evolution but remain frustratingly elusive to direct observation. Ghost galaxies also raise philosophical questions about how we perceive the universe. Our understanding of the cosmos is inevitably shaped by what we can see, and for most of astronomical history, that meant bright, compact objects that stand out against the darkness. But as our technological capabilities have advanced, we've discovered that much of the universe's structure exists in the realm of the barely perceptible, in diffuse systems that hover at the threshold of detection. This has happened throughout the history of astronomy. The Andromeda Galaxy, clearly visible to the naked eye, has been observed for over 1,000 years. But it wasn't until the 1920s that astronomers realized it was a separate galaxy outside the Milky Way. The cosmic microwave background, the most perfect blackbody radiation ever measured, went undetected until 1965, despite filling the entire universe. How many other cosmic phenomena remain undiscovered simply because they don't announce themselves with bright lights or distinct boundaries? Ghost galaxies remind us that the universe is often subtle in its grandeur. Not everything proclaims its existence with blazing starlight or spectacular cosmic fireworks. Some of the most profound structures in the cosmos whisper rather than shout, revealing themselves only to those with the patience and technology to listen for the faintest echoes. And sometimes, these whispers can tell us more than the shouts. Ultra-faint dwarf galaxies, with their extraordinary dark matter to normal matter ratios, may be our best laboratories for studying the properties of dark matter. Ultra-diffuse galaxies, with their paradoxical combination of large size and low density, challenge our models of galaxy formation and evolution. Dark galaxies, rich in gas but poor in stars, may preserve conditions similar to those in the early universe, before most cosmic gas had been processed through stars. Perhaps the most haunting aspect of ghost galaxies is their fate. Many are destined to fade even further as their stars age and die, with no new stars forming to replace them. The ultra-faint dwarfs orbiting the Milky Way will eventually be torn apart by tidal forces, their stars dispersed into the galactic halo. The ultra-diffuse galaxies in cluster environments will continue their slow dimming as their elderly stellar populations evolve toward their end states. The dark galaxies may eventually collide with larger systems, their gas finally forming stars, but in the context of a new galactic environment, rather than as independent entities. In this sense, ghost galaxies are truly ephemeral structures, cosmic echoes in the process of fading away. They represent a transitional phase in the life cycle of cosmic matter, a stage between the primordial gas clouds of the early universe and the complete assimilation of their material into larger cosmic structures. They are the universe forgetting itself, but not completely, leaving behind faint traces that dedicated observers can still detect and study. As astronomical surveys push deeper into the realm of the barely detectable, we'll likely discover many more ghost galaxies lurking in the cosmic shadows. Each will tell a story of formation and evolution under unusual circumstances, of matter that assembled into galaxies but followed a different path than the bright spirals and ellipticals that dominate our cosmic atlases. Collectively, they'll help us piece together a more complete history of the universe, one that includes not just the cosmic main sequence of typical galaxy evolution, but also the outliers, the exceptions, the systems that whisper rather than shout. And perhaps, in studying these fading echoes, we'll gain a deeper appreciation for the ephemeral nature of all cosmic structures. Even the brightest galaxies will eventually dim as their stars age and die. Even the largest clusters will disperse as the universe continues its acceleration. In the far future, all galaxies will become ghost galaxies, fading embers in an increasingly dark and empty cosmos. The ghosts we observe today are not aberrations, but harbingers, early examples of the fate that awaits all cosmic structures in the distant future. What lies in the spaces between the stars? For centuries, astronomers believed the vast gulfs separating stellar systems were essentially empty, mere voids through which light traveled unimpeded. But we now know these cosmic oceans are anything but empty. They are filled with an ethereal substance so delicate and diffuse that it remained hidden from our instruments until relatively recently. This is cosmic dust, the universe's most overlooked storyteller. Cosmic dust consists of tiny solid particles, most smaller than a micrometer across, roughly 1/100th the width of a human hair. Though minuscule in size, these dust grains are ubiquitous, found everywhere from the space between stars to the spiral arms of galaxies, from the vicinity of newborn planetary systems to the outer reaches of the cosmos. Made primarily of carbon, silicon, oxygen, iron, and other common elements, these tiny particles might seem insignificant, yet they hold extraordinary power to shape our view of the universe and preserve its history. Unlike the ephemeral nature of light, or the transparent passage of gravitational waves, dust interacts with radiation in particularly revealing ways. It absorbs, scatters, and re-emits light, transforming visible and ultraviolet radiation from stars into infrared and submillimeter wavelengths. This property makes dust both an obstacle and a tool for astronomers. It obscures our view of distant objects, but also records and retransmits information that would otherwise be lost. Consider what happens when a grain of cosmic dust encounters starlight. The dust absorbs this energy, heating up in the process. This warmed particle then radiates this energy back into space, primarily in the infrared portion of the spectrum. What was once the brilliant blue-white light of a massive star becomes the subtle red glow of heated dust. This process effectively creates an echo, a delayed and transformed repetition of the original stellar emission. These dust echoes can be spectacularly visible in regions of active star formation. In the Orion Nebula, just 1,500 light-years from Earth, massive young stars illuminate vast clouds of gas and dust, creating a celestial light show visible even to the naked eye. The distinctive reddish glow that surrounds these stars is largely the product of dust re-emitting absorbed starlight. Each dust grain captures a portion of the star's energy, then releases it again, creating a diffuse glow that outlines the nebula's complex structure. But dust does more than simply absorb and re-emit light. It also scatters incoming radiation, preferentially reflecting shorter wavelengths like blue light, while allowing longer wavelengths like red light to pass through more easily. This selective scattering is responsible for the brilliant blue color of reflection nebulae, like those surrounding the Pleiades star cluster. The dust in these regions acts like a cosmic mirror, reflecting the blue components of starlight toward our telescopes, while allowing the redder wavelengths to continue their journey through space. This scattering process creates another type of echo, one that preserves some of the properties of the original light, but alters its direction and composition. It's as though the universe is filled with countless tiny mirrors, each reflecting a fragment of the cosmic story in slightly altered form. The role of dust as a cosmic historian becomes even more apparent when we consider its lifespan. Unlike the stars that illuminate it, dust can persist for billions of years, drifting through interstellar space and accumulating information about its surroundings. Each grain carries the chemical imprint of its formation and subsequent journey, providing clues about processes that may have occurred millions or even billions of years in the past. Where does this dust come from? The answer reveals another layer of cosmic echoes. Most cosmic dust forms in the outer atmospheres of dying stars, particularly red giants and supergiants. As these aging stars shed their outer layers, the expelled gas cools and condenses into tiny solid particles. These particles are then blown into interstellar space by stellar winds, or more catastrophic events like supernova explosions. This means that much of the dust we observe today was once inside stars that no longer exist. When we detect infrared radiation from cosmic dust, we're not just seeing an echo of current starlight. We're also observing the physical remnants of stars that may have died billions of years ago. The dust itself is an echo, a material memory of stellar generations long past. Perhaps the most poignant example of dust as a stellar echo comes from observations of supernova 1987A, which exploded in the Large Magellanic Cloud, a satellite galaxy of our Milky Way. Several years after the initial explosion, astronomers detected a brightening ring of light surrounding the supernova site. This was not new emission from the supernova itself, but light from the original explosion, finally reaching a spherical shell of dust that had been expelled by the star thousands of years before it exploded. Like sound echoing off distant canyon walls, the light from the supernova was reflected by this ancient dust back toward Earth, arriving years after the direct light from the explosion. This light echo allowed astronomers to study the supernova explosion from multiple angles and at different times, providing insights impossible from the direct observation alone. But dust does more than passively record and reflect. It plays an active role in one of the universe's most fundamental processes, the formation of new stars and planets. In the cold depths of interstellar clouds, dust provides a surface on which atoms and molecules can accumulate and react. Hydrogen atoms that might otherwise never meet in the vastness of space can find each other on the surface of a dust grain, combining to form molecular hydrogen, the primary fuel for star formation. As gravity slowly compresses these clouds, the dust within them becomes more concentrated. Eventually, in the densest regions, the dust helps shield the growing clumps of gas from external radiation, allowing them to cool and collapse further. Without dust, this cooling would be far less efficient, and the formation of stars like our Sun might proceed very differently, if at all. The dust in these collapsing clouds carries its own history, a record of previous stellar generations encoded in its chemical composition. Elements forged in ancient stars, elements that would later become part of planets and potentially even living things, are preserved in these tiny grains as they participate in the birth of new stellar systems. In this way, dust forms a direct material connection between the stars of the past and those of the future, an unbroken chain of cosmic recycling that stretches back to the earliest generations of stars. Once a new star forms, surrounded by a swirling disk of gas and dust, the dust continues its transformative work. Within this protoplanetary disk, dust grains collide and stick together, gradually growing from microscopic particles to pebbles, then boulders, and eventually planetesimals, the building blocks of planets. The planets of our solar system, including Earth, were formed through this process of dust accumulation roughly 4.6 billion years ago. This means that everything solid around you, including your own body, was once cosmic dust. The carbon in your cells, the oxygen you breathe, the iron in your blood, all were forged in stellar furnaces, expelled into space as gas or dust, and eventually incorporated into the protoplanetary disk that formed our solar system. We are, quite literally, made of stardust that has been recycled through generations of stellar birth and death. The study of dust has revolutionized our understanding of the universe, particularly with the development of infrared astronomy. Because dust emits primarily in the infrared part of the spectrum, telescopes sensitive to these wavelengths can reveal structures invisible to optical instruments. When the Spitzer Space Telescope turned its infrared eyes toward the center of our galaxy, it revealed a landscape hidden from visible light telescopes for centuries. The galactic center, obscured in visible light by thick clouds of dust, comes alive in infrared wavelength. Here we see the chaotic environment surrounding the supermassive black hole at the heart of the Milky Way, with streams of gas and dust being drawn toward this cosmic maelstrom. The dust that prevents visible light from reaching us actually becomes the messenger in infrared, carrying information about regions that would otherwise remain hidden. Even more distant cosmic structures reveal themselves through dust emission. Galaxies undergoing intense bursts of star formation, known as starburst galaxies, are often heavily shrouded in dust. The energetic young stars heat this dust, causing it to glow brightly in infrared. By measuring this dust emission, astronomers can estimate the rate of star formation even when the stars themselves are completely obscured. Some of the most distant galaxies known, observed as they existed when the universe was less than 1 billion years old, have been detected primarily through their dust emission. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is revealing these dust-enshrouded systems in detail, showing that even in the early universe, significant amounts of dust had already formed, challenging our understanding of cosmic chemical evolution. But perhaps the most profound cosmic echo encoded in dust comes from the interstellar medium itself. As dust drifts through the galaxy, it encounters a variety of environments, from the hot, tenuous regions surrounding massive stars to the cold, dense clouds where new stars form. Each environment leaves its mark on the dust, altering its composition, structure, and size distribution. By analyzing the properties of dust in different regions, astronomers can reconstruct its journey and the processes it has experienced. Dust from the outer regions of the galaxy tells a different story than dust near the galactic center. Dust in the spaces between spiral arms carries information about conditions in these less dense regions. Each grain is a miniature time capsule, carrying the accumulated history of its travels through the cosmic ocean. And just as dust preserves the past, it also shapes the future. The dust between stars affects how light travels through the galaxy, influencing the heating and cooling of interstellar gas. This in turn affects where and when new stars will form, setting the stage for the next generation of stellar birth and death. The cosmic dust cycle is a self-regulating system, a feedback loop that helps control the rhythm of galactic evolution. In a universe full of echoes, dust represents something unique. It is not just the carrier of echoes, like light or gravitational waves, but an echo incarnate, a physical remnant of processes long past that continues to influence the cosmic present and future. It transforms the light that passes through it, records the chemistry of its formation, shapes the birth of new stars and planets, and connects generations of stellar life in an unbroken material continuity. As you look up at the night sky, remember that between you and the stars lies a veil of cosmic dust, itself the echo of stars long dead. And within your own body, atoms that once drifted as dust between the stars now form the very essence of your being. We exist within a universe of echoes, but perhaps none are more intimate or profound than those carried by the delicate motes of cosmic dust. What happened to the first stars that ever shone? In the vast tapestry of cosmic history, there are missing threads, luminous beings whose existence we can infer, but whose light we will never directly see. These are the universe's forgotten stars, the first generation that illuminated the cosmic dawn. Though they burned out billions of years ago, their echoes still reverberate through the cosmos in subtle ways, whispering secrets of the early universe to those who know how to listen. The universe was not always filled with stars. For the first few 100 million years after the Big Bang, during what astronomers call the cosmic dark ages, the universe contained only hydrogen, helium, and trace amounts of lithium, distributed almost uniformly through space. There were no heavier elements, no planets, no galaxies, and no sources of visible light. The only radiation was the gradually cooling afterglow of the Big Bang itself, the cosmic microwave background we explored in Chapter 2. But within this darkness, subtle variations in density began to grow under the influence of gravity. Regions slightly denser than average pulled in surrounding material, becoming denser still. Eventually, around 200 million years after the Big Bang, the first protostars began to form at the centers of these collapsing clouds of primordial gas. These first stars, known to astronomers as Population 3 stars, were unlike any that exist in the universe today. Born from pristine gas containing only the lightest elements, they had no metals to facilitate cooling during their formation. This crucial difference led them to be extraordinarily massive, perhaps hundreds of times the mass of our Sun. Modern stars rarely exceed about 150 solar masses, because metal-rich gas cools more efficiently, fragmenting into smaller clouds before collapse is complete. But without metals, the first stars grew to enormous size before ignition. These cosmic giants were also incredibly hot and luminous. A star with 200 times the Sun's mass would shine with the light of nearly 10 million suns. Its surface temperature would exceed 100,000 Kelvin, compared to the Sun's modest 5,800 Kelvin. This meant that Population 3 stars emitted primarily in ultraviolet wavelengths, pumping enormous amounts of high-energy radiation into their surrounding. This radiation began the process of reionization, stripping electrons from the neutral hydrogen atoms that pervaded space. By about 1 billion years after the Big Bang, the radiation from the first generations of stars had transformed the universe from a dark, neutral fog to a transparent plasma through which light could travel freely. This transition from the cosmic dark ages to the era of reionization represents one of the major phase changes in cosmic history. But despite their brilliance, these first stars were destined for short lives. Their enormous mass and high core temperatures caused them to burn through their hydrogen fuel at a prodigious rate. While a star like our Sun will shine steadily for about 10 billion years, the first stars may have exhausted their fuel in just a few million years. A cosmic eye blink. Their deaths were likely as spectacular as their lives. Many would have ended as pair instability supernovae, a rare type of explosion that occurs when the core grows so hot that gamma rays begin to create electron-positron pairs, reducing pressure support and triggering collapse. The resulting explosion completely destroys the star, leaving no remnant behind and ejecting all its material into space. Others might have collapsed directly into black holes, particularly those in the 100 to 250 solar mass range. These first-generation black holes could have been the seeds for the supermassive black holes we now find at the centers of galaxies, objects millions or billions of times the mass of our Sun, that somehow grew to enormous size within the first billion years of cosmic history. Either way, the first stars are long gone. They burned out before the universe was a billion years old, and we now observe the universe at an age of 13.8 billion years. No population 3 star still shines, and their light, traveling through an expanding universe for more than 13 billion years, has been redshifted and diluted to the point of near undetectability. Yet these forgotten stars left echoes that we can still detect today. Perhaps the most direct evidence comes from their chemical legacy. When population 3 stars exploded as supernovae, they seeded their surroundings with the first metals in cosmic history, elements heavier than helium that had been synthesized in their cores or during their explosive deaths. These included carbon, oxygen, nitrogen, silicon, and small amounts of heavier elements like iron. This first generation of metals altered the course of cosmic evolution. Even a small amount of metals dramatically changes how gas cools and collapses to form stars. The next generation of stars, dubbed Population 2, formed from gas lightly enriched with these metals. They were still massive by today's standards, but rarely reached the extreme masses of their Population 3 predecessors. These stars, which formed in the universe's first billion years, still exist today in the halos of galaxies and in globular clusters, ancient stellar groupings that orbit the Milky Way and other galaxies. By studying the chemical composition of these ancient Population 2 stars, astronomers can infer properties of the forgotten Population 3 stars that enriched them. One strategy involves searching for extremely metal-poor stars in our galaxy's halo, objects whose composition might reflect the output of just one or a few Population 3 supernovae. These stellar fossils preserve a chemical record of the first nucleosynthesis in the universe, an echo of stellar alchemy from the cosmic dawn. The star SMSS J2332.541142003.3, discovered in 2018, contains the lowest iron abundance ever measured, less than 1/10,000,000th the iron content of our Sun. Yet it shows relatively high amounts of carbon, indicating it formed from gas enriched by a low-energy supernova from a first-generation star. By modeling the nuclear reactions that must have occurred in that ancient explosion, astronomers can reconstruct properties of the long-vanished progenitor. Another echo of the first stars comes from the cosmic infrared background, a diffuse glow in infrared wavelengths that permeates the universe. Some of this background may represent the highly redshifted light of the first generations of stars, stretched over billions of years from ultraviolet to infrared wavelengths by the expansion of the universe. Like the cosmic microwave background, which preserves information about the Big Bang, the cosmic infrared background may contain encoded information about the universe's first luminous objects. The James Webb Space Telescope, with its unprecedented infrared sensitivity, may be able to detect individual groups of Population 3 stars in the most distant observable galaxies. If successful, this would give us a direct glimpse of the forgotten stars not as they exist today, which they don't, But as they existed over 13 billion years ago, their light just now reaching our telescopes after an epic journey across the expanding universe. But perhaps the most profound echo of the first stars lies in the presence of elements necessary for life. Every atom of carbon in your body, the backbone of organic chemistry, was synthesized inside a star. While most came from generations of stars much later than population 3, those first stellar alchemists began the process of cosmic enrichment that eventually led to planets, complex chemistry, and life. The oxygen you breathe, the calcium in your bones, the iron in your blood, all required stars to forge them. Without the first generation of stellar furnaces and the supernovae that distributed their products through space, the universe would remain a place of hydrogen and helium alone, incapable of supporting the chemical complexity required for life as we know it. Even the structure of the cosmos bears the imprint of these forgotten luminaries. The radiation from the first stars and their deaths as supernovae or black holes affected how matter continued to collapse and form structures. The energy they injected into their surroundings could have delayed the formation of some smaller galaxies while triggering the collapse of others. The pattern of galaxies we see today, with its filaments, clusters, and voids, may partly reflect the influence of the first stars. The earliest black holes, remnants of some population 3 stars, may have merged and grown over cosmic time to become the supermassive black holes now found at the centers of galaxies. These cosmic behemoths, with masses billions of times that of our Sun, pose a puzzle for astronomers, because they appear fully formed in galaxies less than 1 billion years after the Big Bang, seemingly too quick for gradual growth processes. The forgotten stars, with their potential to form black holes of tens or hundreds of solar masses, might provide the seeds needed to explain these early giants. Another echo may be found in cosmic reionization itself. Observations suggest this process was patchy and extended, with some regions of the universe becoming transparent before others. The specifics of how this phase transition unfolded, still being mapped by astronomers, depend on the properties, distribution, and timing of the first luminous sources. Each bubble of ionized gas that expanded around a population 3 star, or cluster of stars, has long since merged with others, but the pattern of when and where reionization occurred preserves information about those first sources of light. Even primordial gravitational waves, ripples in spacetime from the first instance after the Big Bang, may have been affected by the first stars. As these waves traveled through the early universe, they would have interacted with the changing distribution of matter as the first stars formed, lived, and died. This interaction might have left subtle imprints that could, in principle, be detected by future gravitational wave observatories. The forgotten stars also connect to one of the greatest mysteries in modern cosmology, the nature of dark matter. This invisible substance, which makes up about 85% of the matter in the universe, provided the gravitational scaffolding within which the first stars formed. The size, distribution, and timing of these first stellar generations depend sensitively on the properties of dark matter particles. By constraining when and how the first stars formed, astronomers can narrow down the range of possible dark matter candidates. Perhaps most poetically, the forgotten stars represent the universe's first light in another sense. They were the first objects to break the symmetry of the nearly uniform early cosmos. Before them, matter was distributed almost evenly, with only subtle variations in density. The first stars represented a dramatic departure from uniformity, concentrating matter and energy into brilliant points of light amid the darkness. They were the universe's first experiment in creating complex, non-uniform structures, the beginning of a process that would eventually lead to galaxies, planets, and observers. We will likely never know exactly how many population 3 stars formed, or precisely when and where the very first one ignited. These details are lost to time, erased by the subsequent 13 billion years of cosmic evolution, but their collective influence remains, encoded in the chemistry, structure, and radiation of the universe we observe today. In this sense, the forgotten stars are not truly forgotten. Though their light has ceased, their echoes continue to shape our cosmos. They are like ancestors whose names we no longer remember, but whose genes we still carry. Their legacy lives on in every heavy element, in the black holes lurking at galactic centers, in the very possibility of planets and life. As we look to the future of astronomy, with more powerful telescopes and more sensitive detectors for all forms of radiation, we may yet find more direct evidence of these cosmic pioneers. The James Webb Space Telescope might glimpse their light from the edge of the observable universe. Gravitational wave observatories might detect the mergers of black holes created in the deaths of population 3 stars. Advanced computer simulations may reconstruct their lives and deaths in ever greater detail. But even without these direct observations, the forgotten stars remain an essential chapter in the cosmic story. They transformed the universe from its simple beginnings of hydrogen and helium into the chemically rich, structurally complex cosmos we inhabit today. Their brief lives and spectacular deaths set the stage for everything that followed, including our own existence. In a universe filled with echoes, some of the most profound are those of stars, whose light ceased to shine when the cosmos was still in its infancy. Though forgotten by name, their influence continues, a whisper from the cosmic dawn that reaches us even now, 13 billion years later. Have you ever considered that when you look up at the night sky, you're not just looking across space, but also back in time? Every beam of starlight reaching your eyes has been traveling for years, decades, centuries, or even millions of millennia. The universe has arranged itself into the ultimate time machine, with ancient light streaming toward us from every corner of the cosmos, carrying messages from different epochs simultaneously to our tiny planet. This concept sounds almost magical, yet it's a fundamental truth of astronomy. When you observe the bright star Sirius in the winter sky, you're seeing it as it existed 8.6 years ago. The light from the Andromeda Galaxy, visible as a faint smudge to the naked eye on dark nights, left its source 2.5 million years ago, when our early human ancestors were just beginning to walk upright in Africa. The most distant galaxies observable with our most powerful telescopes appear to us as they were more than 13 billion years ago, when the universe was in its infancy. This is not because we're looking through some kind of cosmic wormhole or employing science fiction technology. It's simply because light, though incredibly fast, is not infinitely so. It travels at approximately 300,000 kilometers per second, a speed that allows it to circle Earth nearly 8 times in a single second. Yet the universe is so vast that even at this blazing velocity, light takes significant time to cross the gulfs between stars and galaxies. The light year, a distance measure that astrophysicists commonly use, encapsulates this relationship between space and time. 1 light year equals the distance light travels in a year, about 9.46 trillion kilometers. When astronomers say a star is 100 light years away, they mean both that the star is 946 trillion kilometers distant and that we're seeing it as it was 100 years ago. Distance and time are inextricably linked in our view of the cosmos. This means that the universe we observe is not the universe as it exists now, but rather a complex overlay of different time periods, all arriving at our telescopes simultaneously. It's as though we're watching a movie where each pixel on the screen is playing at a different point in the timeline. Nearby stars might be minutes or years in the past, while distant galaxies represent scenes from billions of years ago. This phenomenon creates a peculiar kind of cosmic memory. Events that have already concluded continue to be observable as their light travels outward through space. A star might have exploded 1,000 years ago, but if it was 5,000 light years away, we won't witness its supernova for another 4,000 years. The information about that explosive death is already en route to us, traveling through the void at light speed, an unstoppable messenger from the past. Consider the star Eta Carinae, one of the most massive and luminous stars in our galaxy, located about 7,500 light years away. In the 1840s, Astronomers observed it brightening dramatically in what we now call the Great Eruption, becoming briefly the second brightest star in the night sky despite its great distance. What they were actually witnessing was an event that had occurred around the time that early humans were creating the first cave paintings in Europe. Even more striking is the fact that we don't know if Eta Carinae still exists. It might have already exploded as a supernova or collapsed into a black hole, but we wouldn't know yet because the light from such an event wouldn't have reached us. We're 7,500 years behind in our observations of this stellar giant. For all we know, a dazzling supernova light show from Eta Carinae might already be en route to our planet, silently traveling through space to arrive at some future date. This temporal delay affects everything we observe in the universe. The center of our own Milky Way galaxy lies about 27,000 light-years from Earth. When we look toward the galactic core, we're seeing it as it was when human civilization was just beginning to develop agriculture during the Neolithic period. The light from any event happening there now won't reach us until the year 29,000 CE. Our Sun, the closest star to Earth, is so near that this effect might seem negligible. Light from the Sun takes only about 8 minutes and 20 seconds to reach us. Yet even this creates a curious situation. If the Sun were to somehow instantly disappear, we wouldn't know about it for those 8 minutes. Earth would continue orbiting the gravitational center where the Sun used to be, bathed in the light of a star that no longer existed, until the last rays reached us and darkness fell. This light travel time creates what astronomers call the observable universe, the spherical region of space from which light has had time to reach us since the beginning of the cosmos. Beyond this cosmic horizon lie regions whose light hasn't had enough time to arrive at Earth. These distant realms exist, but we cannot see them. The observable universe is not the whole universe, but merely the portion from which light has had time to reach us in the 13.8 billion years since the Big Bang. And this observable sphere is expanding. Each day, light from slightly more distant regions reaches us for the first time. The observable universe grows by 1 light day in radius every day. Yet, paradoxically, many galaxies we currently observe will eventually disappear from our view. Due to the accelerating expansion of the universe, their light will be stretched to undetectable wavelengths, and they will fade from our cosmic picture like ships sailing over the horizon. When we observe the most distant detectable galaxies, we're seeing them not just as they were billions of years ago, but also in a much smaller, denser universe. The early cosmos was dramatically different from the one we inhabit today. Galaxies were closer together, more irregular in shape. By studying these ancient light sources, astronomers can reconstruct the evolution of cosmic structure over time, watching as the universe transforms from its chaotic youth to its more ordered present state. This ancient light also reveals how the elements necessary for life emerged gradually over cosmic history. The very first stars and galaxies contained almost exclusively hydrogen and helium, the elements created in the Big Bang. Heavier elements like carbon, oxygen, and iron, essential for planets and life, were forged inside stars and distributed through space when those stars exploded. By observing galaxies at different distances, and thus different times in the past, astronomers can track the increasing abundance of these heavy elements, a process called cosmic chemical evolution. Sometimes, the ancient light reaching us has taken a circuitous route. When light from a distant galaxy passes near a massive foreground galaxy, its path can be bent by gravity, a phenomenon called gravitational lensing. This cosmic lens can create multiple images of the background galaxy, each showing it at slightly different times. In some cases, the difference can be months or years. This means astronomers can sometimes witness the same cosmic event multiple times as light from it arrives along different paths bent by gravity. This lensing effect serves as a natural telescope, magnifying the light from some of the most distant objects in the observable universe. The massive galaxy cluster MACS J0647 JA17015, for instance, lenses the light from a galaxy called MAX 0647 JD, allowing us to see it as it existed just 420 million years after the Big Bang. Without this gravitational magnification, this ancient galaxy would be too faint for even our most powerful telescopes to detect. The ancient light streaming toward us includes more than just the visible wavelengths our eyes can detect. The full electromagnetic spectrum, from radio waves to gamma rays, carries information about different aspects of cosmic sources. Radio waves reveal the distribution of hydrogen gas and the presence of energetic phenomena like pulsars and quasars. Infrared light can penetrate dust clouds, showing us regions of star formation hidden from optical telescopes. X-rays and gamma rays expose the most energetic processes in the universe, from matter spiraling into black holes to the explosive deaths of massive stars. Each wavelength tells a different part of the cosmic story, and together they form a comprehensive picture of the universe across time. Modern astronomical observatories often observe the same region of sky in multiple wavelengths, creating composite images that reveal the full complexity of cosmic structures. Perhaps the most profound example of ancient light comes from the cosmic microwave background, which we explored in Chapter 2. This faint glow, coming from all directions in space, represents light released when the universe was just 380,000 years old. It has been traveling through space for 13.8 billion years, gradually stretched by cosmic expansion until its original visible wavelengths now fall in the microwave portion of the spectrum. This is truly ancient light, a baby picture of the universe preserved for all time. The fact that this primordial light comes from all directions emphasizes a key point. There is no special direction in the universe. The cosmic microwave background surrounds us in a perfect sphere, with no point in the sky being fundamentally different from any other. When we look in any direction, we're seeing back in time, with distance corresponding directly to how far back in time we're observing. This omnidirectional property of ancient light creates a kind of cosmic onion skin structure around us. Nearby galaxies form the innermost layer, seen as they were in the relatively recent past. More distant galaxies form successive layers, each representing an earlier epoch in cosmic history. The cosmic microwave background forms the outermost layer, the edge of the observable universe. We sit at the center of this nested arrangement, not because we occupy any special position in the universe, but simply because we are the observers, the point to which all this ancient light converges. Another fascinating aspect of ancient light is that it preserves the history of events that might otherwise be invisible to us. When a star explodes as a supernova, the brilliant flash might last only weeks or months, but the light from that explosion continues traveling outward in an expanding shell, eventually reaching planets and other stars. If those objects reflect the light, they can create what astronomers call a light echo, similar to a sound echo bouncing off canyon walls. In 2003, astronomers detected light echoes from supernova 1987A, the closest supernova to Earth in modern times. Light from the initial explosion had traveled outward, encountered dust clouds in the vicinity, and been redirected toward Earth. By studying these echoes, scientists could observe the supernova from different angles, essentially seeing around corners in space-time. Even more dramatically, astronomers have detected light echoes from historical supernovae that occurred hundreds of years ago. By observing light reflected off interstellar dust clouds, they've been able to study the spectra of supernovae that exploded in our galaxy before the invention of the telescope. This is like having a time machine that allows us to study astronomical events long after they've concluded. The universe's ancient light also reveals how fundamentally interconnected everything is, across vast spans of space and time. The atoms in your body, the metals in your devices, the calcium in your bones, all were forged inside stars that existed billions of years ago. The hydrogen in water molecules might be nearly as old as the universe itself. We are made of ancient stellar material, our very existence dependent on processes that occurred long before Earth formed. When you look up at the night sky, you're not just observing distant suns and galaxies. You're witnessing cosmic history unfolding before your eyes, a panoramic view of the universe as it existed across billions of years. Each pinpoint of light tells a story from a different era, arriving simultaneously at your retina in a grand confluence of cosmic timeline. And remarkably, that ancient light is still on the move. The photons that strike your eyes tonight will continue their journey, reflecting off your cornea and scattering into space. Some might travel for billions more years, eventually reaching other worlds around other stars. Perhaps someday, one of those photons will enter the optical sensor of an alien telescope, bringing with it information about Earth as it existed in your lifetime. In this way, light connects everything in the cosmos across unfathomable gulfs of space and time. It carries the memory of events long concluded, preserving them for future observers. It reveals the universe not as a static structure, but as a dynamic, evolving system whose history is written in the ancient light that fills the void, traveling endlessly from past to future, from beginning to end. As you contemplate the night sky, remember that you are not just looking up into space, you are looking back in time. The cosmos your eyes perceive is a ghost, a memory, an echo of what once was. When we think of sound, we typically imagine vibrations traveling through air, water, or solid materials. We think of music, conversation, or the rumble of thunder. But sound, in its most fundamental form, is simply a pressure wave moving through a medium. And remarkably, the early universe itself resonated with such waves. Not in air, but in the hot plasma that filled all of space before stars or galaxies existed. These ancient sound waves, though long since silenced, left an indelible imprint on the structure of the cosmos we observe today. To understand how sound shaped the universe, we must return to its early moments, after the initial inflation but before stars had formed. About 380,000 years after the Big Bang, the universe was filled with an ionized plasma of protons, electrons, and photons, all interacting constantly in a hot, dense fog. In this environment, any slight compression of matter created pressure that pushed back, causing the compressed region to expand, then overshoot and rarefy. These cosmic sound waves, technically called baryon acoustic oscillations, began from the tiny quantum fluctuations that were stretched to macroscopic scales during inflation. Where matter was slightly denser, gravity pulled surrounding material inward, increasing the density further. But this compression heated the plasma, creating outward pressure that pushed back against gravity. This interplay between gravity pulling inward and pressure pushing outward created oscillations that propagated through the primordial plasma, like sound waves through air. The physics of these oscillations was remarkably similar to ordinary sound waves, though the medium was the entire observable universe rather than Earth's atmosphere. Just as sound waves on Earth have a characteristic speed determined by the properties of air, these cosmic sound waves had a well-defined velocity, about 57% the speed of light, determined by the properties of the primordial plasma. For hundreds of thousands of years, these sound waves traveled outward from their points of origin, compressing and rarefying the cosmic medium as they went. The entire universe was ringing like a vast bell, with overlapping waves creating complex patterns in the distribution of matter. But unlike a bell, which can ring indefinitely in the absence of damping, the cosmic sound waves were about to encounter a dramatic change in their medium. When the universe cooled to about 3000 Kelvin, approximately 380,000 years after the Big Bang, electrons could finally combine with protons to form a neutral hydrogen atom. This event, called recombination, fundamentally altered the physics of the cosmos. The formerly charged plasma became a neutral gas, and photons, which had been constantly scattering off free electrons, could suddenly travel unimpeded through space. This transition effectively switched off the pressure support that had allowed sound waves to propagate. The oscillations froze in place, with regions of compression and rarefaction locked into the distribution of matter. It was as though a cosmic conductor had suddenly silenced the universal orchestra, leaving the final note hanging in space. The pattern created by these frozen sound waves would prove remarkably durable. As the universe continued to expand and evolve, gravity slowly enhanced the density contrasts created by the acoustic oscillations. Regions that were slightly denser than average became the seeds for cosmic structures. Over billions of years, these seeds grew into the vast cosmic web we observe today, with galaxies concentrated along filaments and sheets, separated by relatively empty voids. But how do we know these ancient sound waves existed? The evidence comes from two complementary observations of the cosmos. The first is the cosmic microwave background, the relic radiation from the hot early universe that we've discussed in previous chapters. When scientists map the tiny temperature variations in this background, they're essentially seeing a snapshot of the sound waves as they existed at the moment of recombination. These temperature fluctuations can be analyzed mathematically using a technique called power spectrum analysis, which breaks down complex patterns into their component wavelength. When this analysis is applied to the cosmic microwave background, it reveals a series of peaks and troughs at specific angular scales, exactly matching what we would expect from sound waves that had been oscillating since the Big Bang. The first peak in this spectrum corresponds to regions that had time to compress once before recombination froze the oscillations. The second peak represents regions that had time to compress, then rarefy, their oscillation caught in the opposite phase. The third peak shows regions that completed 1.5 oscillations, and so on. By measuring the positions and heights of these peaks, cosmologists can determine fundamental properties of the universe, including its geometry, the amount of dark matter, and the amount of normal or baryonic matter. The second line of evidence comes from surveys of galaxy positions in the relatively nearby universe. Although individual galaxies have moved significantly since the early universe, the overall statistical pattern of their distribution still preserves the imprint of the primordial sound waves. Specifically, if you measure the probability of finding two galaxies separated by various distances, you find a slight excess at a separation of about 500 million light-years. This characteristic distance, called the sound horizon, represents how far the acoustic waves could travel before recombination silenced them. Finding this same scale imprinted in both the cosmic microwave background and the distribution of galaxies provides powerful confirmation that our understanding of cosmic evolution is on the right track. What makes these cosmic sound waves particularly fascinating as echoes is that they connect the quantum fluctuations of the infant universe directly to the large-scale structure we observe today. The pattern of galaxies across billions of light-years emerged from sound waves that were once small enough to fit within a subatomic particle, before inflation stretched them across the cosmos. The waves themselves are long gone, silenced when the universe cooled enough for neutral atoms to form, but their memory persists in the arrangement of every cluster of galaxies, every filament of the cosmic web, every void between structures. The entire architecture of the visible universe bears the imprint of these ancient oscillations. Imagine holding a seashell to your ear and hearing what seems to be the sound of ocean waves. What you're actually hearing is the resonance of ambient noise within the shell's cavity. In a similar way, when astronomers map the cosmos, they're hearing the lingering resonance of primordial sound waves, preserved in the distribution of galaxies across space. These baryon acoustic oscillations also provide cosmologists with a standard ruler for measuring the expansion history of the universe. Because we know the physical size of the sound horizon from fundamental physics, we can use its apparent size at different cosmic epochs to track how the universe has expanded over time. This technique has become a powerful tool for investigating dark energy, the mysterious force accelerating the universe's expansion. Recent galaxy surveys have detected the baryon acoustic oscillation signal with increasing precision. Projects like the Baryon Oscillation Spectroscopic Survey BOSS and its successor eBOSS have measured the positions of millions of galaxies to create three-dimensional maps of the cosmos, spanning billions of light years. These maps reveal the subtle imprint of sound waves from the infant universe preserved across cosmic time. Future surveys will push these measurements to new precision, potentially revealing whether dark energy has changed over time, or whether Einstein's theory of gravity requires modification on the largest scales. The echoes of primordial sound waves may thus hold the key to some of the greatest unsolved mysteries in modern cosmology. But the cosmic sound waves did more than just shape the large-scale distribution of galaxies. They also influenced the formation of the very first luminous objects. After recombination, the universe entered the cosmic dark ages, a period when no stars yet existed to illuminate the void. During this time, the density fluctuations left by the acoustic oscillations continued to grow under the influence of gravity. In regions where matter was slightly more concentrated, gravity drew in additional material, eventually forming the first protogalaxies. These early cosmic structures formed preferentially at the peaks of the sound wave pattern, their positions determined by oscillations that had ceased hundreds of thousands of years earlier. When the first stars ignited within these protogalaxies, their light began to reionize the neutral hydrogen that filled the universe, gradually bringing the cosmic dark ages to an end. This process, called reionization, was complete by about 1 billion years after the Big Bang. But the pattern of reionization, with some regions becoming transparent before others, was influenced by the underlying distribution of the first galaxies, which in turn reflected the frozen sound waves from the primordial plasma. In this way, even the transition from a dark universe to a transparent one bears the imprint of those ancient acoustic oscillations. The cosmic sound waves shaped not just where structures would form, but when different regions would emerge from darkness into light. It's worth noting that the cosmic sound waves were not the only oscillations present in the early universe. Gravity waves, oscillations in space-time itself propagating at the speed of light, also traversed the primordial cosmos. These would have left their own distinctive pattern in the cosmic microwave background, potentially offering a window into the inflationary epoch that preceded the hot Big Bang. Unlike the acoustic oscillations, which required the matter radiation plasma as a medium, gravitational waves propagate through empty space. They would have continued uninterrupted when the universe transitioned from plasma to neutral gas at recombination. Their imprint would be seen primarily in the polarization of the cosmic microwave background, creating a distinctive B-mode pattern that scientists have been searching for with increasingly sensitive instruments. If detected, these primordial gravitational waves would provide the ultimate cosmic echo, carrying information from the first fraction of a second after the beginning of time. They would confirm the theory of inflation and potentially reveal the energy scale at which it occurred, offering unprecedented insight into the physics of the very early universe. But even without this gravitational wave detection, the acoustic oscillations provide a remarkable connection between the microscopic and the macroscopic, between the quantum fluctuations of the early universe and the galaxies and galaxy clusters we observe today. They remind us that the cosmos, for all its current silence, was once filled with the resonance of enormous pressure waves, moving energy and matter in patterns that would eventually guide the formation of every structure we see. The universe's acoustic period was brief by cosmic standards, lasting only 380,000 years in a universe that has existed for 13.8 billion years. But in that relatively short time, sound waves shaped the destiny of matter across the cosmos, creating a blueprint for structure that would unfold over billions of years of subsequent evolution. Today, the universe is too diffuse for sound waves to propagate over astronomical distances. The average density of matter in intergalactic space is less than 1 atom per cubic meter, far too tenuous to support acoustic oscillations. True cosmic silence has fallen, but the memory of that ancient resonance remains, encoded in the positions of galaxies and the pattern of the cosmic microwave background. In this sense, the entire observable universe serves as a fossil record of those primordial sound waves, a cosmic phonograph preserving the last note of a symphony that fell silent billions of years ago. When cosmologists map the distant universe, they are reading this record, translating the positions of countless galaxies into information about the acoustic physics of the early cosmos. And remarkably, what they find matches precisely what our theoretical models predict, confirming our understanding of how the universe evolved from its hot, dense beginnings to the vast, cool cosmos we inhabit today. The sound waves that once filled all of space have long since fallen silent, but their echo continues to shape every galaxy, every cluster, every supercluster across the billions of light years of the observable universe. What happens when a star collapses so completely that nothing, not even light, can escape its gravitational pull? The result is a black hole, perhaps the most enigmatic object in the universe. These cosmic abysses seem to represent the ultimate erasure of information, regions where matter and energy disappear behind an event horizon, seemingly lost forever to the observable universe. Yet, paradoxically, black holes may be among the most perfect record keepers in the cosmos, preserving the memory of everything that has fallen into them in subtle and surprising ways. To understand how black holes maintain memories, we must first understand their nature. A black hole forms when matter is compressed so densely that the escape velocity exceeds the speed of light. According to Einstein's general relativity, this occurs because matter and energy curve spacetime, and extreme concentrations create such profound curvature that space essentially folds in upon itself, forming a region from which nothing can emerge. The boundary of this region is called the event horizon, the point of no return beyond which escape becomes impossible. From the outside, we can never observe what happens inside this boundary. It's as though the black hole draws a veil across a portion of the universe, hiding its contents from external observers. Yet, despite this apparent amnesia, black holes retain certain properties that provide clues about their formation and history. The first is mass. Every black hole has a precise mass that reflects all the matter and energy that has fallen into it throughout its existence. When stars, gas, dust, or even other black holes are consumed, their mass is added to the black hole's total. In this fundamental way, black holes keep a running tally of everything they've devoured. The second property is spin, or angular momentum. Just as Earth rotates on its axis, black holes can spin, sometimes at rates approaching the speed of light at their event horizons. This rotation reflects the accumulated angular momentum of all the material that has fallen in. If a black hole forms from a rotating star, it inherits that rotation. If it consumes matter that orbits in a particular direction, that orbital motion is converted to black hole spin. The third property is electric charge. While most astrophysical black holes are thought to be electrically neutral, in principle, a black hole could carry a net electric charge if it consumed more positively than negatively charged particles, or vice versa. This charge would create an electromagnetic field around the black hole, detectable from the outside. Remarkably, according to the no-hair theorem of general relativity, these three properties, mass, spin, and charge, completely characterize a black hole. All other details about the matter that formed it or fell into it are seemingly erased. Whether a black hole forms from a collapsed star, a cloud of pure hydrogen, or a collection of vintage automobiles, once the material crosses the event horizon, all distinguishing characteristics appear to vanish. This led to a profound puzzle in theoretical physics. If black holes erase all information about the matter that forms them, what happens to the fundamental principle that information cannot be destroyed? This principle, rooted in quantum mechanics, suggests that if you knew the exact state of every particle in the universe, you could in principle run the laws of physics backward and reconstruct the entire cosmic history. But black holes seem to introduce irreversible amnesia into the universe, creating what became known as the black hole information paradox. The The resolution to this paradox may lie in the subtle ways black holes preserve memories of what falls into them. The first hint came from Stephen Hawking's groundbreaking work in the 1970s. Hawking demonstrated that, contrary to classical expectations, black holes are not completely black. Due to quantum effects near the event horizon, they emit a faint radiation, now called Hawking radiation. This radiation arises when quantum fluctuations create pairs of particles and antiparticles near the event horizon. Normally, these pairs would quickly annihilate each other, but occasionally, one particle falls into the black hole while the other escapes. To conserve energy, the escaping particle carries away positive energy, while the infalling particle must have negative energy. This negative energy reduces the black hole's mass, causing it to slowly evaporate over time. Initially, Hawking believed this radiation was completely thermal, containing no information about what had fallen into the black hole. This would mean that when a black hole fully evaporated, all information about its contents would be irretrievably lost, violating the conservation of information. But subsequent work by Hawking and others suggested that the radiation might be subtly encoded with information after all. The current understanding, still an active area of research, suggests that Hawking radiation is actually entangled with the interior of the black hole in extremely complex ways. The radiation appears random and thermal to simple measurements, but if one could somehow capture and analyze all the radiation emitted throughout a black hole's lifetime, it might in principle be possible to reconstruct everything that ever fell in. This would mean that black holes don't actually destroy information, but rather store it in a highly scrambled form, gradually releasing it through Hawking radiation over unimaginable timescales. A stellar mass black hole might take 10 to the 67th power years to fully evaporate, far longer than the current age of the universe. But given enough time, every black hole would eventually return all the information it had absorbed, preserving the fundamental principles of quantum mechanics. Even before evaporation, black holes leave imprints of their history in their surroundings. When matter falls toward a black hole, it typically doesn't plunge directly in, but forms an accretion disk, a swirling maelstrom of superheated gas circling the event horizon. This gas emits intense radiation across the electromagnetic spectrum before finally crossing the point of no return. The patterns in this radiation can reveal details about the black hole's mass and spin, as well as the composition and dynamics of the infalling material. X-ray telescopes like NASA's Chandra and NuSTAR observe these emissions from black holes throughout our galaxy, reading the energetic signals from matter in its final moments before disappearing from the observable universe. For spinning black holes, another memory effect emerges from what physicists call frame dragging. The rotation of the black hole literally drags space-time around with it, like a spinning ball in honey. Any object that enters this region, called the ergosphere, is forced to rotate in the same direction as the black hole. This effect extends the black hole's influence beyond its event horizon, imprinting its rotational history on the surrounding space-time. Black holes also remember their past through the structure of space-time around them. Each black hole creates a distinctive gravitational well, like a deep dimple in the fabric of space. The exact shape of this dimple depends on the black hole's mass, spin, and charge. As objects orbit the black hole, they follow paths determined by this curved space-time, carrying information about the black hole's properties in their trajectories. When black holes merge, as detected through gravitational waves by LIGO and Virgo observatories, they create distinctive ripples in space-time. The precise pattern of these ripples depends on the masses and spins of the merging black holes. By analyzing these gravitational wave signals, astronomers can reconstruct details about the black holes that produce them, reading their masses and spins from the echoes they leave in the fabric of space-time itself. Perhaps the most dramatic demonstration of how black holes preserve memory comes from recent efforts to directly image them. In 2019, the Event Horizon Telescope, a global network of radio observatories, captured the first image of a black hole's shadow from the supermassive black hole at the center of galaxy M87. This shadow, cast against the glowing backdrop of the accretion disk, reveals the black hole's mass and spin, properties that encapsulate its growth history over billions of years. In 2022, a similar effort produced an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This object, with a mass of about 4 million suns, has grown over billions of years by consuming stars and gas cloud. Its current size and rotation reflect this long history of cosmic meals, a memory of everything it has devoured since it first formed in the early universe. Indeed, supermassive black holes are particularly powerful cosmic historians. Found at the centers of nearly all large galaxies, these behemoths, weighing millions to billions of solar masses, grow primarily by consuming gas and stars from their host galaxies, as well as by merging with other black holes during galaxy collisions. The final mass of each supermassive black hole reflects this complex history of growth. Remarkably, astronomers have discovered tight correlations between the masses of these central black holes and properties of their host galaxies, such as the velocity dispersion of stars in the galactic bulge. This relationship, known as the M-sigma relation, suggests a coevolution of black holes and galaxies, with each influencing the other's development over cosmic time. This means that by measuring a galaxy's central black hole, astronomers can infer aspects of that galaxy's evolutionary history. Conversely, by studying the galaxy, they can estimate properties of the black hole. The two are inextricably linked, each preserving information about the other through their gravitational relationship. Some supermassive black holes become active galactic nuclei when they consume matter at high rates. The infalling material heats up and creates jets of particles that can extend for millions of light years. These jets can persist for millions or even billions of years, carrying information about the feeding patterns of the central black hole far out into intergalactic space. Long after the feeding frenzy has subsided, these jets remain as fossils, echoing the black hole's past activity. Even dormant black holes leave their mark on surrounding star clusters. As stars orbit the central black hole of a galaxy, they occasionally pass close enough to be torn apart by tidal forces, creating what astronomers call a tidal disruption event. These catastrophic stellar destructions release enormous amounts of energy, briefly illuminating the otherwise dark black hole. The frequency and characteristics of these events depend on the black hole's mass and the stellar population around it, providing another window into its history. Stars that survive close encounters with black holes don't emerge unchanged. Their orbits are altered, sometimes dramatically, by the gravitational interaction. By mapping the motions of stars near a black hole, astronomers can reconstruct aspects of the black hole's growth history and the dynamical evolution of the surrounding stellar cluster. At the center of our Milky Way, astronomers have tracked individual stars orbiting Sagittarius A star for over 2 decades. These stellar orbits have revealed not just the black hole's mass, but also constraints on its spin and on the possible presence of smaller black holes in its vicinity. Each star's path carries information about the central gravitational well, reading and transmitting the black hole's properties through its motion. Another way black holes preserve memory is through their merger history. When two black holes merge, the final black hole typically has a different spin than either of its progenitors. This new spin reflects the original spins and the orbital angular momentum of the merging system. By measuring the spin of a black hole, astronomers can potentially infer whether it formed from a single collapsing star or from the merger of previous black holes. This spin signature is particularly important for understanding the origin of intermediate mass black holes, objects with masses between 100 and 100,000 times that of our Sun. These might form through the successive mergers of smaller black holes in dense star clusters. If so, they would tend to have high spins aligned with their most recent merger event, a memory of their growth history encoded in their rotation. But perhaps the most profound way black holes maintain memory is through the fundamental properties of gravity itself. According to general relativity, the gravitational field outside a black hole depends only on its mass, spin, and charge, regardless of what went into making it. This might seem to suggest that black holes erase information, But in a deeper sense, the gravitational field is the information stored in the very fabric of space-time. Every particle that falls into a black hole leaves its mark on this gravitational field. The changes might be imperceptibly small for individual particles, but they are there in principle, encoded in the precise curvature of space-time. The black hole remembers, not through conventional means, but through the fundamental structure of reality itself. This perspective aligns with a concept in modern physics called the holographic principle, which suggests that all the information contained within a volume of space can be encoded on its boundary. Applied to black holes, this would mean that all information about what has fallen in is somehow recorded on the event horizon, like data written on the surface of a cosmic hard drive. The mathematics supporting this view emerges from string theory and quantum gravity, where black holes are reinterpreted as extraordinary information processing systems. Rather than destroying information, they may be the ultimate compression algorithm, taking three-dimensional objects and encoding their complete quantum description on a two-dimensional surface. But even if this theoretical resolution of the information paradox is correct, practical recovery of information from a black hole remains beyond any conceivable technology. The encoding is so complex, the timescales for Hawking radiation so vast, that for all practical purposes, what falls into a black hole is lost to our observation. Yet the universe itself keeps the books balanced. Nothing is truly forgotten at the fundamental level, merely transformed and encoded in ways that exceed our current capacity to decode. Black holes, rather than being cosmic amnesiacs, may be the universe's most perfect record keepers, preserving every detail of their formation and growth in the subtle language of gravity, a language we are only beginning to understand. As we continue to observe black holes through various astronomical means, X-ray emissions from accretion disks, gravitational waves from mergers, direct imaging of shadows, stellar orbits in their vicinity, we are learning to read portions of this gravitational record. Each observation reveals another aspect of how black holes preserve the memory of everything that has fallen into them throughout cosmic history. In this way, black holes represent the ultimate cosmic echo. Long after stars have burned out, after galaxies have dispersed, after even atoms have decayed, black holes will remain, silently preserving the memory of everything they have consumed. And eventually, through the unimaginably slow process of Hawking radiation, they will return this information to the universe, whispering their secrets back into the void over timescales that dwarf the current age of the cosmos. For now, we can only glimpse fragments of these memories through our observations. But in these fragments, we find echoes of cosmic events long past, preserved in the most extreme objects the universe has to offer. Cosmic librarians keeping perfect records through the language of curved spacetime. What will be the final whispers of our cosmos? We've explored how the universe preserves its history through light, gravitational waves, cosmic dust, and the imprint of ancient sound waves. We've journeyed from the first moments after the Big Bang to the present day. But what of the future? What final echoes will reverberate through space when stars no longer shine and galaxies have dissolved into the expanding void? To contemplate the ultimate fate of the universe is to enter a realm where timescales stretch beyond human comprehension. We must think not in thousands or millions or even billions of years, but in trillions, quadrillions, and numbers so vast they dwarf the current age of the cosmos. This is the domain of physical eschatology, the study of how the universe will evolve in its distant future. Our universe today is vibrant and luminous. Stars forge heavy elements in their cores, galaxies collide and merge, black holes feast on surrounding matter, creating brilliant accretion disks and powerful jets. Cosmic rays streak through space at nearly the speed of light. Gravitational waves ripple through the fabric of space-time, with each merger of compact objects. The cosmos resonates with energy across all wavelengths of the electromagnetic spectrum, but this era of cosmic vibrancy won't last forever. The universe is evolving, and the evidence suggests it's evolving toward silence, toward darkness, toward an ever fainter series of final echoes, stretching across unimaginable timescales. The first major transition will occur in about 100 trillion years, as the last stars exhaust their nuclear fuel. Stars form from collapsing clouds of gas, primarily hydrogen, which fuses into helium and releases energy in the process. In more massive stars, helium can further fuse into carbon, oxygen, and heavier elements. But eventually, all stars run out of fusible material. Their nuclear fires extinguish, and depending on their mass, they end as white dwarfs, neutron stars, or black holes. New star formation continues today because vast reservoirs of hydrogen gas remain available. But this gas isn't infinite. In about 100 trillion years, the last wisps of free hydrogen will have been incorporated into stars or dispersed so widely by cosmic expansion that new star formation will cease entirely. The universe will witness the birth of its final star, the last new light in an increasingly dark cosmos. The existing stars will continue to shine for a time. The smallest red dwarfs, with masses about 8% that of our Sun, burn their fuel so slowly and efficiently that they can shine for up to 10 trillion years. But even these miserly stars eventually exhaust their hydrogen. One by one, the lights of the cosmos will wink out, never to be replaced. As stars die, they leave behind stellar remnants. The least massive stars leave white dwarfs, Earth-sized balls of degenerate matter supported against further collapse by quantum mechanical effects. More massive stars explode as supernovae, leaving behind neutron stars, city-sized balls of neutrons so dense that a teaspoonful would weigh billions of tons. The most massive stars collapse into black holes, regions where gravity is so strong that nothing, not even light, can escape. For a time, these stellar remnants will continue to emit energy. White dwarfs and neutron stars form incredibly hot, slowly cooling over trillions of years as they radiate their thermal energy into space. Even after they no longer produce visible light, they'll continue to emit infrared radiation, then microwave, then radio, their dying whispers stretching across incredible spans of time. As stars die and galaxies darken, the night sky, as seen from any surviving planets, will gradually empty. Where once thousands of stars were visible to the naked eye, there will be hundreds, then dozens, then just a handful of nearby stellar embers. Eventually, even these will fade, leaving utter darkness. Any surviving observers would see only the dim glow of neighboring galaxies, themselves growing darker with each passing eon. The darkening of the stars represents the end of the stelliferous era, the age of stars that has dominated the universe since about 20 million years after the Big Bang. This era will have lasted for approximately 100 trillion years, about 10,000 times longer than the universe's current age. But in the full scope of cosmic future, it will come to seem like just a bright flash at the beginning of time, a brief moment when nuclear fusion illuminated the cosmos before eternal darkness set in. As the universe continues to age, even the remaining stellar remnants will begin to disappear. Over timescales of 10 to the power of 26 years, roughly 100 million trillion years, proton decay may begin to erode ordinary matter. According to some theoretical models, protons, the building blocks of atomic nuclei, are not perfectly stable but decay with an unimaginably long half-life. If this theory proves correct, all protons will eventually decay into lighter particles, disintegrating the atomic nuclei that form the basis of ordinary matter. White dwarfs, composed primarily of carbon and oxygen, would slowly dissolve as their constituent atoms decayed, releasing small amounts of energy with each disintegration. This process would take so long that a white dwarf would emit less energy than a firefly, but it would continue for timeframes that make the current age of the universe seem like the blink of an eye. Even if protons are perfectly stable, white dwarfs face an eventual demise. Over timescales of 10 to the power of 32 years, roughly 10 trillion years, Quantum tunneling will cause the electrons in white dwarfs to combine with protons, converting these stellar remnants into neutron stars. This process, undetectably slow by human standards, represents another whisper in the dying universe, another echo fading over cosmological timescales. Neutron stars themselves will eventually collapse into black holes through similar quantum mechanical processes, though this would take even longer, perhaps 10 to the power of 100 years. By this time, the universe will have expanded so dramatically that each black hole will likely occupy its own observable universe, unable to interact with any other matter or radiation. Black holes, those cosmic librarians preserving the memory of everything that has fallen into them, will become the dominant objects in the universe during this era. Yet even they are not eternal. As Stephen Hawking discovered, black holes emit radiation through quantum effects near their event horizons. This Hawking radiation causes black holes to lose mass and eventually evaporate entirely. The evaporation timescale depends on the black hole's mass. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate, billions of trillions of times longer than the current age of the universe. Supermassive black holes with millions or billions of solar masses would last even longer, up to 10 to the power of 100 years. As each black hole approaches the end of its existence, it will shine more brilliantly through its Hawking radiation. In its final moments, it will release a burst of high-energy particles, a final echo of everything that ever fell into it throughout its long existence. These terminal bursts, separated by unimaginable gulfs of time and expanding space, will represent some of the last structured energy releases in the history of the cosmos. The evaporation of the last black hole will mark the end of the black hole era and the beginning of the dark era, when the universe will consist almost entirely of elementary particles, photons, neutrinos, electrons, and positrons, all separated by ever-increasing distances as cosmic expansion continues. These particles will occasionally interact, producing brief flashes of energy that quickly dissipate into the void. One such interaction would be the rare collision of an electron and positron, which annihilate to produce gamma rays. Another would be the decay of dark matter particles, if they prove unstable over these timescales. Each such event would represent a tiny echo in an otherwise silent cosmos, a momentary disruption in the universe's inexorable slide toward maximum entropy. In this dark era, lasting from 10 to the power of 100 years to essentially infinity, the universe will approach a state that physicists call heat death. All energy will be evenly distributed, with no concentration that could perform work or emit structured radiation. The temperature will approach absolute zero as space continues to expand, diluting what little energy remains to near nothingness. Yet even in this seemingly dead state, quantum fluctuations will continue. According to the uncertainty principle, even empty space experiences tiny fluctuations in energy, creating and annihilating virtual particles over incredibly brief timescale. In the vast emptiness of the far future universe, these quantum flickers will represent the last activity in an otherwise static cosmos. And here we encounter a remarkable possibility, a potential final echo that could, in principle, reset the cosmic clock. Given enough time frames so vast they make all the periods we've discussed seem instantaneous, quantum fluctuations might randomly generate new structures. In an infinite future, even the most improbable events eventually occur. One such possibility is the spontaneous formation of a Boltzmann brain, a conscious entity arising from random fluctuations. Another is the nucleation of a false vacuum bubble that could trigger a phase transition in the vacuum of space itself, potentially initiating a new Big Bang within our dead universe. These prospects remain highly speculative, representing the outer edge of theoretical physics rather than firm predictions. If our universe has a flat or hyperbolic geometry, as current measurements suggest, then cosmic expansion will continue forever, and the scenario outlined above represents our best understanding of the far future. But there are alternative possibilities worth considering, other ways the cosmic symphony might conclude. If dark energy, the mysterious force accelerating cosmic expansion, changes its properties over time, the universe's fate could be dramatically altered. If dark energy strengthens, a scenario called the Big Rip could tear apart all structures, from galaxy clusters down to atoms and subatomic particles, as the expansion rate becomes infinite in a finite time. In this case, the last echoes would be the sequential disintegration of cosmic structures, a cascading series of destructions concluding with the dissolution of elementary particles themselves. Conversely, if dark energy weakens or reverses sign, becoming attractive rather than repulsive, the universe could eventually halt its expansion and begin contracting. This would lead to a big crunch, the opposite of the Big Bang, where all matter and energy collapse to a singularity. The last echoes in this scenario would be the merger of galaxies, stars, and planets as space itself contracted, concluding with unimaginably energetic conditions similar to the early universe. Some theoretical models suggest a cyclic universe, where the Big Crunch leads to a new Big Bang, creating a new cosmos with potentially different physical laws. Others propose that our universe is one bubble in a vast multiverse, with new universes constantly nucleating in the space between existing ones. In these scenarios, the final echoes of our universe might form the first sounds of the next, an eternal cosmic respiration of expansion and contraction. But returning to the most widely accepted model, based on current observations, we face a universe slowly fading to silence over timescales that dwarf human comprehension. In this scenario, what meaning can we find in these final, ever fainter echoes? Perhaps the most profound insight comes from considering what these echoes represent. Each fading white dwarf, each evaporating black hole, each quantum fluctuation in the dark future carries information about what came before. The radiation from a cooling neutron star contains encoded data about the supernova that formed it and the massive star that exploded. The Hawking radiation from an evaporating black hole theoretically preserves information about everything that ever fell into it. In this sense, the universe never truly forgets. Even as structures dissolve and energy disperses, information persists, encoded in increasingly subtle patterns. The cosmos may grow silent, but its memory endures in the precise arrangement of its fading components. A whispered story told over trillions upon trillions of years. This perspective offers a kind of cosmic consolation. The stars and galaxies we observe today, the planets and moons of our solar system, even our own brief lifesoul leave imprints that persist long after their visible manifestations have vanished. Nothing is truly lost to the universe, merely transformed and encoded in ways that become increasingly difficult to read as entropy increases and complexity diminishes. The far future universe will be unimaginably different from the one we inhabit. Where now we see brilliance and activity, future epochs will know only darkness and near stasis. Yet this transition from vibrant complexity to quiet simplicity represents not a failure, but the natural evolution of a cosmos governed by fundamental physical laws. And remarkably, those laws themselves appear finely tuned to allow for the brief but magnificent flowering of complexity we now witness. Had physical constants been slightly different, the universe might have recollapsed seconds after the Big Bang, or expanded so rapidly that no structures could form. Instead, we inhabit a cosmos that, for a brief window in its enormous lifespan, supports stars, planets, and the emergence of life. This window of complexity, this middle chapter in the cosmic story between the chaos of the Big Bang and the silence of the Dark Era, represents something precious. We exist during the universe's most interesting period, when energy gradients support complex structures, when stars forge heavy elements, when life can arise on rocky planets circling main sequence stars. Our ability to contemplate the universe's far future, to project the consequences of physical laws across timescales that dwarf our existence, represents one of the most remarkable achievements of the cosmos itself. Through human consciousness, the universe has developed the capacity to model its own evolution, to hear its future echoes before they sound, to imagine its own ending. In the words of physicist Freeman Dyson, it is impossible to calculate in detail the long-range future of the universe without including the effects of life and intelligence. It is impossible to calculate the capabilities of life and intelligence without touching, at least peripherally, philosophical questions. If we are to examine how intelligent life may be able to guide the physical development of the universe for its own purposes, we cannot altogether avoid considering what the values and purposes of intelligent life may be. This suggests an intriguing possibility. Perhaps the ultimate fate of the universe is not predetermined solely by physical laws, but might be influenced by the intelligent life it spawned. Future civilizations, with technologies far beyond our current comprehension, might develop ways to manage entropy locally, to preserve structures against the cosmic tide of dissolution, or even to initiate new regions of cosmic evolution. Such speculations reach beyond established science into the realm of the long-term future of intelligence. Yet they remind us that the universe's story remains unfinished, that the echoes yet to sound might be shaped not just by blind physical processes, but by conscious entities working to preserve complexity against the pull of entropy. Whatever the ultimate fate of our cosmos, whether eternal expansion or cyclic rebirth, whether heat death or something yet unimagined, the echoes it generates carry the memory of everything that has occurred, from the first instance after the Big Bang to the evaporation of the last black hole, from the formation of the first hydrogen atoms to the final quantum fluctuations in near-empty space. The universe preserves its history in the subtle patterns of energy and matter that persist across deep time. As we gaze at the night sky, we witness ancient light from distant sources, echoes from billions of years in the cosmic past. Future observers, should they exist, will someday look back at our epoch as an ancient time of brightness and activity, a period when the cosmos rang with the energy of nuclear fusion, gravitational collapse, and electromagnetic radiation across all wavelengths. The universe's final whispers may be faint beyond detection, separated by gulfs of time and space that dwarf our comprehension. Yet they represent the continuation of a story that began with the Big Bang, a story written in light and gravity, in atoms and stars, in galaxies and voids, a story whose middle chapters include the emergence of life and consciousness on at least one small planet orbiting an ordinary star. In this vast cosmic narrative, our brief moment of awareness allows us to hear the echoes of the universe's past and to imagine those of its future. We exist in a cosmos that knows itself, however imperfectly, through the minds that have evolved within it. And in that knowledge, in that connection between consciousness and cosmos, we find perhaps the most remarkable echo of all the universe reflecting upon itself, a circle of awareness closing across billions of years of evolution. As the final stars fade, as the last black holes evaporate, as quantum fluctuations become the only disruption in an otherwise static void, this legacy of consciousness may represent the universe's most enduring echo, a memory of complexity and awareness preserved in the subtle patterns of a cosmos slowly approaching perfect silence. Have you ever wondered how cosmic structures communicate across the vast emptiness of space? Galaxies, those immense islands of stars, gas, and dust, are not isolated entities drifting silently through the void. They speak to one another through invisible bridges, dance in gravitational embraces, and send messages across millions of light years. The universe is engaged in a grand conversation, with galaxies as its primary conversationalists, and the language they speak shapes the evolution of the cosmos itself. Galaxies first communicate through gravity, the most fundamental and far-reaching force in the universe. Every galaxy creates a gravitational field that extends infinitely outward, growing weaker with distance, but never truly disappearing. These gravitational fields overlap and interact, creating complex networks of influence that can span hundreds of millions of light years. Through these invisible tendrils, galaxies pull on one another, altering each other's trajectories and internal dynamics even when separated by enormous gulfs of empty space. Consider our own local group, a collection of more than 54 galaxies dominated by the Milky Way and Andromeda. These two spiral galaxies, separated by about 2.5 million light-years, are engaged in a slow gravitational dance that will eventually lead to their collision about 4.5 billion years from now. Their mutual gravitational attraction has been drawing them together for billions of years, a silent conversation conducted through the curvature of space-time itself. This gravitational dialogue isn't limited to neighboring galaxies. Vast structures called galaxy superclusters, spanning hundreds of millions of light-years. These superclusters create the largest known structures in the universe, arranged in a cosmic web of filaments and sheets, surrounding relatively empty voids. This web itself represents a kind of frozen conversation, a record of how gravity has transmitted information about the distribution of matter across cosmic distances over billions of years. But gravity is just the beginning of how galaxies communicate. When galaxies come close enough to interact directly, they speak to each other through tidal forces, stretching and distorting each other's structures in ways that astronomers can observe. These tidal interactions create spectacular features like bridges of stars and gas connecting nearby galaxies, or long tails streaming away from galaxies that have experienced close encounters. The Antennae galaxies, located about 60 million light-years from Earth, demonstrate this tidal conversation vividly. This pair of colliding galaxies has developed long streaming arms of stars and gas that extend far beyond their main bodies, giving them an appearance reminiscent of insect antennae. These structures formed as the galaxy's mutual gravity pulled material outward, creating visible evidence of their ongoing interaction. Similarly, the Mice galaxies, another pair in the process of merging, display dramatic tails that stretch tens of thousands of light-years into intergalactic space. These tails aren't merely passive features but active regions where new stars form and complex chemistry unfolds. The tidal conversation between these galaxies isn't just reshaping their structures, but catalyzing new creation within the distorted regions. Sometimes the gravitational dialogue between galaxies can be more subtle. The Milky Way's beautiful spiral structure may partly result from past interactions with smaller satellite galaxies. As these smaller systems orbit our galaxy or fall into it, they create ripples and waves in the disk of stars, helping to organize and maintain the spiral pattern. Even the Milky Way's central bar, a straight structure of stars crossing the galactic core, may have been enhanced or shaped by these gravitational conversations. Galaxies also communicate through direct exchanges of material. When galaxies collide or pass near each other, they can transfer substantial amounts of gas, dust, and even stars from one to another. This material exchange can dramatically affect both galaxies, providing fresh gas to fuel star formation in one, while stripping the other of the resources needed to create new stars. The Large and Small Magellanic Clouds, satellite galaxies of the Milky Way visible from the southern hemisphere, demonstrate this material dialogue. A vast stream of hydrogen gas, called the Magellanic Stream, extends from these galaxies across more than 100 degrees of the sky. This stream represents gas being pulled from the Magellanic Clouds by the Milky Way's gravity, a transfer of material that will eventually provide our galaxy with resources for forming new stars. Sometimes galaxies don't just exchange material but actively steal it. A process called Ram pressure stripping occurs when a galaxy falls into a galaxy cluster and encounters the hot, diffuse gas that fills the cluster's intergalactic space. As the galaxy moves through this medium, the pressure strips away its own gas, creating long trails visible in X-ray observations. These trails can extend for hundreds of thousands of light years, visible markers of an ongoing cosmic theft. Galaxy cluster Abell 2125, located about 3 billion light-years from Earth, shows numerous galaxies experiencing this RAM pressure stripping. The hot gas filling the cluster acts like a cosmic wind, blowing away the cooler gas from galaxies moving through it. This stripping effectively halts star formation in the affected galaxies, demonstrating how the cluster environment can fundamentally alter a galaxy's evolutionary path through this harsh form of communication. Perhaps the most dramatic form of galactic conversation occurs when galaxies fully merge. When two similarly sized galaxies collide at relatively low speeds, they don't bounce off each other but pass through one another, their stars largely avoiding direct collisions due to the vast empty space between them. However, their gas clouds do collide, and their gravitational fields interact strongly, distorting both galaxies and eventually drawing them back together for additional passages. After several such passages, the galaxies lose their distinct identities and merge into a single system. If the original galaxies were spirals rich in gas, the resulting merger often forms an elliptical galaxy, with a rounder, smoother structure lacking the spirals of its progenitors. This transformation represents one of the primary ways galaxies evolve, a conversion from one type to another through direct interaction. The galaxy NGC 7252, nicknamed the Atoms for Peace galaxy, shows the late stages of such a merger. Located about 220 million light-years away, this system still displays tidal tails from the original collision, but the main bodies of the merging galaxies have coalesced into a single structure. In about 1 billion years, the tails will either fall back into the galaxy or disperse into intergalactic space, and NGC 7252 will appear as a normal elliptical galaxy, with only subtle clues to its violent formation. Beyond these visible exchanges, galaxies communicate through radiation, sending light across the cosmos that can influence distant systems. Active galactic nuclei, powered by supermassive black holes accreting matter at galactic centers, can produce jets of particles and radiation that extend for millions of light-years. These jets can interact with other galaxies, or with the intergalactic medium, transferring energy across vast distances. Centaurus A, a peculiar galaxy about 12 million light-years from Earth, displays enormous radio jets extending more than 1 million light-years from its center. These jets, propelled by the galaxy's central black hole, inject energy into the surrounding intergalactic medium, affecting how gas cools and forms structures in that region of space. Through these jets, Centaurus A broadcasts its presence across millions of light-years, influencing the evolution of gas and potentially other galaxies in its vicinity. Similarly, when massive stars within galaxies explode as supernovae, they create expanding shells of radiation that can travel for vast distances. These radiation fronts carry both energy and information about the chemical composition of the exploding stars. When they encounter gas clouds in the same or even different galaxies, they can trigger compression and cooling, potentially catalyzing new star formation. This radiative conversation extends beyond individual events to the collective output of entire galaxies. Some galaxies, called starburst galaxies, experience periods of extraordinarily rapid star formation, often triggered by interactions with other galaxies. During these starbursts, the galaxies shine brilliantly, particularly in infrared wavelengths, and pump energy and newly synthesized elements into the surrounding intergalactic medium. Galaxy M82, located about 12 million light-years away in the constellation Ursa Major, exemplifies this starburst phenomenon. Its interaction with neighboring galaxy M81 has triggered intense star formation, causing M82 to radiate energy at a rate much higher than typical for its size. The collective stellar winds and supernova explosions from its newly formed massive stars drive a galactic superwind, propelling hot gas, enriched with heavy elements, into intergalactic space at hundreds of kilometers per second. Through these various modes of communication, gravitational, tidal, material exchange, mergers, and radiation, galaxies participate in an ongoing cosmic conversation that shapes their evolution and the structure of the universe at the largest scales. But this conversation isn't uniform across cosmic history. It has changed dramatically over the universe's lifetime, reflecting the evolving conditions of cosmic expansion. In the early universe, galaxies were closer together due to the smaller scale of cosmic expansion. This proximity made interactions more frequent and more intense. Observations of distant galaxies, seen as they appeared billions of years ago, reveal systems that are often irregular, disturbed, and clearly interacting. The cosmic conversation was louder, more chaotic, with galaxies exchanging material and energy at a much higher rate than we observe locally today. As the universe expanded and the average distance between galaxies increased, this conversation generally became quieter and less frequent, though no less transformative when it occurred. In the modern universe, most large galaxies show signs of past mergers and interactions, preserved in their structures, star populations, and distribution of elements. Each galaxy carries the memory of these past conversations, a record of who they've spoken with across billions of years. Our own Milky Way bears these conversation marks. Its halo contains streams of stars that originated in smaller galaxies consumed by our own. Its disk shows ripples and warps that record past gravitational disturbances. Even the chemical composition of its stars preserves information about past episodes of gas accretion and star formation triggered by interactions. Our galaxy's current structure and composition represents the cumulative result of billions of years of conversation with its cosmic environment. The supermassive black hole at the Milky Way's center, Sagittarius A star, likely grew to its current mass of about 4 million solar masses, partly through galaxy mergers. When galaxies merge, their central black holes eventually find each other and coalesce, combining their masses. The relatively modest size of our galaxy's central black hole suggests that the Milky Way hasn't undergone many major mergers with similarly sized galaxies, though it has certainly consumed numerous smaller systems. This ongoing exchange between galaxies ensures that none evolve in isolation. Even galaxies in seemingly empty regions of space feel the gravitational influence of distant mass concentrations and are bathed in radiation from far-off sources. The universe functions as an interconnected system, with information and influence flowing across enormous distances through various carriers. Computer simulations of cosmic evolution dramatically illustrate this interconnectedness. When cosmologists model the growth of structure from the early universe to the present, they find that small initial density fluctuations evolve into a complex cosmic web through the gravitational conversations between matter concentrations. The resulting structure, with its characteristic filaments, sheets, and voids, emerges from these gravitational exchanges without needing any special initial conditions. These simulations also reveal how galaxy clusters form at the intersections of cosmic filaments, where material flowing along multiple filaments converges. These clusters represent the densest conversation spaces in the universe, regions where dozens or hundreds of galaxies interact simultaneously through all the mechanisms we've discussed. Within clusters, galaxies experience accelerated evolution, their properties transformed more rapidly than in less dense environments. The Coma Cluster, located about 330 million light-years from Earth, exemplifies this dense conversation space. Containing thousands of galaxies packed into a region about 20 million light-years across, Coma subjects its member galaxies to intense gravitational interactions, ram pressure stripping, and radiation exposure. As a result, the cluster contains a higher proportion of elliptical and lenticular galaxies, systems that have been stripped of their gas. The conversations between galaxies don't just affect their individual evolution, but also influence the intergalactic medium itself. The space between galaxies isn't empty, but filled with diffuse gas, much of it heated to millions of degrees by energy input from galaxies. This gas, called the Warm-Hot Intergalactic Medium, WIM, contains a significant fraction of the universe's ordinary matter and bears the chemical imprint of billions of years of galactic outflows. When galaxies expel gas through supernovae, active galactic nuclei, or other processes, they enrich the intergalactic medium with elements heavier than hydrogen and helium. These elements, forged in stellar furnaces and explosive stellar deaths, spread through intergalactic space and can eventually fall back into the same or different galaxies to be incorporated into new generations of stars and planets. This cosmic recycling represents a form of chemical communication, with galaxies contributing to and drawing from a shared reservoir of elements. The metallicity of a galaxy, its abundance of elements heavier than helium, reflects both its internal history of star formation and its conversations with the surrounding environment through gas exchanges. The most dramatic example of this chemical communication comes from observations of enormous bubbles of hot gas extending above and below the Milky Way's disk. These structures, discovered relatively recently, extend about 25,000 light-years from the galactic plane and appear to have been created by a period of intense activity around our galaxy's central black hole several million years ago. These Fermi bubbles, named after the gamma-ray telescope that first detected them, represent a kind of broadcast from the Milky Way's center, carrying energy and chemically enriched material far into the galactic halo. Similar structures have been observed around other galaxies, suggesting that such energetic announcements are a common feature of galactic evolution. As we look toward the future, the conversation between galaxies will continue to evolve. Our local group is gradually consolidating, with smaller galaxies being consumed by the Milky Way and Andromeda. Eventually, these two spiral giants will merge, their billions of stars combining to form a large elliptical galaxy that astronomers have whimsically named Milkomeda. This merger, expected in about 4.5 billion years, will dramatically transform both galaxies. Their spiral structures will be disrupted, their gas will be compressed to trigger intense star formation, and their central black holes will eventually merge. The resulting elliptical galaxy will be larger than either progenitor, but will gradually exhaust its gas supply, becoming a red and dead system with little new star formation. On even longer time scales, the accelerating expansion of the universe due to dark energy will fundamentally alter the cosmic conversation. Galaxies beyond our local group will recede at ever-increasing speeds, eventually moving faster than light relative to us, due to the expansion of space itself. This will place them beyond our cosmic horizon, their light unable to ever reach us. Within our gravitationally bound local group, the conversation between galaxies will continue, but in increasing isolation from the wider universe. After about 100 billion years, astronomers in Milkomeda would see only a handful of nearby dwarf galaxies beyond their own. The distant universe, with its billions of galaxies and rich large-scale structure, would become invisible, its light stretched beyond detection by cosmic expansion. This gradual silencing of the wider cosmic conversation represents one of the profound consequences of dark energy. Future civilizations might have no observational evidence for other galaxy clusters, for the cosmic web, or for the universe's expansion. The rich dialogue between distant cosmic structures that we can currently observe will fade from view, leaving only local exchanges between gravitationally bound systems. Yet even as the visible universe contracts to our local cosmic neighborhood, the echoes of past galactic conversations will remain encoded in the structure, composition, and dynamics of the remaining systems. Each galaxy preserves its history of interactions in its stellar populations, its chemical makeup, and its structural features. Through careful study, future astronomers could still reconstruct aspects of the wider cosmic dialogue, even when direct evidence has disappeared beyond the horizon. What is the music of the spheres? Ancient philosophers imagined the heavenly bodies creating harmonious sounds as they move through the cosmos. While literal celestial music remains poetic license, the universe does operate according to profound rhythmic patterns, cycles that repeat across vastly different scales, from atomic vibrations to galactic rotations. These cosmic rhythms compose a grand symphony that has been playing since the birth of time, a complex arrangement of tempos and frequencies that together form the heartbeat of our universe. The most fundamental cosmic rhythm emerges from the vibration of elementary particles themselves. According to quantum field theory, particles aren't static objects, but excitations in underlying fields, oscillating at specific frequencies. An electron, for instance, has a natural frequency, or Compton frequency, of about 10 to the power of 20 Hz, an unimaginably rapid oscillation that defines its very existence. Heavier particles oscillate even faster, while particles of light, photons, represent pure electromagnetic waves with frequencies that determine their energy and color. These quantum rhythms form the universe's most rapid tempos, the allegro prestissimo of the cosmic symphony. They occur everywhere, in all matter and energy, serving as the foundation upon which all larger structures and slower rhythms are built. Though we cannot directly perceive these frequencies with our senses, they underlie everything we see, touch, and measure. Moving up in scale, atoms pulsate with their own characteristic frequencies. When electrons in atoms transition between energy levels, they absorb or emit photons with precise frequencies corresponding to the energy difference. These frequencies create the unique spectral fingerprints astronomers use to identify elements in distant stars and galaxies. Each element in the periodic table contributes its own set of frequencies to the cosmic orchestra, a distinctive voice that can be detected billions of light years away. Hydrogen, the most abundant element in the universe, resonates at multiple frequencies, including the famous 21-centimeter line created when the spin of its electron flips relative to its proton. This particular rhythm, with a frequency of 1420 MHz, has special significance for astronomy. It penetrates dust clouds that block visible light, allowing us to map the distribution of hydrogen throughout our galaxy and in distant systems. This single frequency has revealed the spiral structure of the Milky Way and traced the rotation of countless other galaxies. As atoms combine to form molecules, new vibrational and rotational rhythms emerge. Molecular clouds in interstellar space pulse with these frequencies, detectable as emission or absorption lines in radio and infrared wavelength. Water, carbon monoxide, ammonia, and dozens of more complex molecules each contribute their characteristic frequencies to the cosmic spectrum, creating a rich molecular music that fills our galaxy. Complex organic molecules found in interstellar space, some containing dozens of atoms, vibrate at lower frequencies in the microwave and radio portions of the spectrum. These molecules, potentially important for the origins of life, create their own subtle rhythms in the dark clouds where stars and planets form. Each molecular species adds its voice to the cosmic composition, a complex chord of frequencies that reveals the chemical richness of the universe. As we scale up to larger structures, stars pulsate with various rhythms. Many stars vibrate like enormous bells, expanding and contracting in regular patterns. These stellar pulsations come in different varieties, from the rapid oscillations of dwarf stars, completing cycles in minutes or hours, to the slow breathing of red giants, with periods of months or years. Cepheid variable stars, named after the prototype Delta Cephei, pulsate with such reliable periods that astronomers use them as cosmic distance markers. The relationship between a Cepheid's pulsation period and its intrinsic brightness allows us to measure distances to galaxies millions of light years away. Each Cepheid beats with its own tempo, a stellar metronome marking time across the cosmos. RR Lyrae stars, another class of pulsating variables, oscillate with periods of about half a day. These ancient stars, often found in globular clusters, create a characteristic rhythm that has continued without interruption for billions of years. Their pulsations, driven by the periodic ionization and recombination of helium in their outer layers, represent one of the universe's most reliable timekeepers. Some stars display multiple overlapping pulsation patterns, creating complex rhythmic structures similar to polyrhythms in music. By analyzing these overlapping oscillations, astronomers can probe the internal structure of stars through a technique called astroseismology, reading the star's interior properties from its surface vibrations. The Sun, our local star, vibrates with millions of different oscillation modes simultaneously. These solar oscillations, with periods around 5 minutes, are caused by sound waves trapped within the Sun's interior. By measuring these vibrations, solar astronomers can essentially listen to the Sun's interior, much as seismologists use earthquake waves to study Earth's internal structure. Binary star systems create longer rhythmic cycles as stars orbit their common center of mass. These orbital periods range from hours for the closest binaries to thousands of years for widely separated pairs. In some cases, the orientation of these systems relative to Earth causes one star to periodically eclipse the other, creating regular dips in brightness that reveal the system's dynamics. Algol, a famous eclipsing binary in the constellation Perseus, dims noticeably every 2.87 days when its fainter companion passes in front of the brighter primary star. This rhythm was noticed by ancient astronomers who named the star after a demon, Al-Ghul, due to its unsettling periodic winking. Today we understand this cosmic rhythm as the precise orbital dance of two stars, separated by just a few million kilometers. When stars die, they can create some of the most precise rhythms in the universe. Pulsars, rapidly rotating neutron stars, emit beams of radiation that sweep past Earth like cosmic lighthouses. The fastest pulsars, called millisecond pulsars, rotate hundreds of times per second, with some maintaining such precise timing that they rival the best atomic clocks on Earth. PSR B1937 GR121, the first millisecond pulsar discovered, rotates 642 times per second, its lighthouse-like beam sweeping past Earth, with a regularity that varies by less than a nanosecond over months of observation. This extraordinary precision allows pulsars to serve as cosmic timepieces, enabling tests of general relativity and potentially providing a galactic navigation system for future interstellar missions. Moving to planetary scales, our own solar system operates according to various orbital rhythms. Earth circles the Sun every 365.256 days, while simultaneously rotating on its axis every 23.934 hours. These two fundamental cycles create the rhythm of days and years that have governed life on our planet for billions of years. Earth's rotation is gradually slowing due to tidal interactions with the Moon, lengthening the day by about 1.7 milliseconds per century. This means that during the dinosaur era, days were significantly shorter than they are now, demonstrating how even seemingly fixed cosmic rhythms evolve over geological timescales. The Moon orbits Earth every 27.322 days, creating monthly cycles that influence Earth's tides, some animal behaviors, and many human cultural calendars. The alignment of the Sun, Earth, and Moon creates the rhythm of lunar phases, with full moons occurring every 29.531 days, as the Moon completes its synodic orbit relative to the Sun. More complex rhythms emerge from interactions between different orbital periods in our solar system. Earth's axis wobbles like a spinning top in a 26,000-year cycle called precession, causing the position of the north celestial pole to trace a circle among the stars. This precession, combined with changes in Earth's orbital eccentricity and the tilt of its axis, creates the Milankovitch cycles that influence long-term climate patterns and ice ages. The planets in our solar system create their own rhythmic relationships. Jupiter and Saturn, the two largest planets, come into approximate alignment every 19.85 years, a cycle that repeats with slight variations. Over longer periods, the gravitational interactions between planets create resonances and near resonances that stabilize or destabilize orbits. A complex gravitational music that has shaped the architecture of our solar system over its 4.5 billion-year history. Some of these planetary rhythms create visible effects. The hexagonal storm at Saturn's North Pole rotates with a period of about 10 hours and 39 minutes, driven by atmospheric circulation patterns that have maintained this geometric structure for decades or longer. Jupiter's Great Red Spot, a storm larger than Earth, has been swirling for at least 400 years, completing a rotation about every 6 days. Beyond our solar system, exoplanets orbit their host stars with periods ranging from less than a day to hundreds of years. These distant worlds create their own complex systems of orbital resonances and cycles. The famous TRAPPIST, one system contains 7 roughly Earth-sized planets, with orbital periods forming near-perfect mathematical ratios to each other, a cosmic harmony reminiscent of the music of the spheres, imagined by ancient astronomers. Scaling up further, entire galaxies rotate with their own stately rhythms. The Milky Way completes one rotation at our Sun's distance from the center in about 230 million years. This galactic year represents the time it takes our solar system to make one complete circuit around the galactic center, a journey of about 150,000 light-years through the spiral arms of our island universe. Since the Earth formed about 4.5 billion years ago, our solar system has completed only about 20 of these galactic years. The last time we were at this approximate position in the galaxy, dinosaurs had not yet evolved. By the time we complete another galactic year, humans in our current form will almost certainly no longer exist, replaced by whatever our species evolves into over the coming hundreds of millions of years. The spiral arms themselves are not fixed structures, but density waves that move through the galactic disk, similar to ripples on a pond. Stars and gas clouds move through these waves, becoming compressed and triggering star formation. This creates a rhythm of stellar birth as material passes through spiral arms, a galactic heartbeat with a period of tens of millions of years. Beyond individual galaxies, galaxy pairs and groups create their own orbital periods. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, orbit our galaxy with periods of about 1.5 billion and 2.5 billion years, respectively. Their gravitational interaction with each other and with the Milky Way creates complex tidal patterns that distort all 3 galaxies and generate the Magellanic Stream, a long trail of gas connecting these systems. On the largest scales, galaxy clusters contain thousands of galaxies orbiting their common center of mass, with periods of hundreds of millions or billions of years. These enormous structures represent the largest bound objects in the universe, their members locked in gravitational orbits that will continue long after individual stars have burned out. Even the universe as a whole expands with its own rhythm. The Hubble parameter, which measures the rate of cosmic expansion, changes over time as the universe evolves. In the early universe, the expansion was slowing due to the gravitational attraction of matter. But about 5 billion years ago, the influence of dark energy became dominant, causing the expansion to accelerate. This changing cosmic tempo, from decelerating to accelerating expansion, represents perhaps the grandest rhythm in nature, the fundamental beat of space-time itself. These cosmic rhythms, from the quantum vibrations of elementary particles, to the stately rotation of galaxies, to the accelerating expansion of the universe, form a nested hierarchy of cycles, each influencing and being influenced by the others. Together, they create a cosmic symphony of extraordinary complexity and beauty, a multi-layered composition that has been playing since the birth of time and will continue long after humanity has disappeared. What makes these cosmic rhythms particularly fascinating is how they interact across different scales. The 11-year solar cycle, during which the sun's magnetic field reverses polarity and sunspot activity waxes and wanes, influences Earth's upper atmosphere and potentially aspects of our climate. The 26,000-year precession of Earth's axis affects which stars appear at the north and south celestial poles, changing the night sky over millennial timescales. The 100,000-year Milankovitch cycle caused by variations in Earth's orbital eccentricity, correlates with the major ice age cycles of the past million years. These astronomical rhythms become encoded in Earth's geological record, preserved in ice cores, seafloor sediments, and stalagmites. By reading these natural archives, scientists can track how cosmic cycles have influenced our planet's climate and environment over hundreds of thousands or millions of years. Even life itself operates according to various rhythms that often synchronize with cosmic cycles. The daily cycle of light and darkness drives circadian rhythms in organisms from bacteria to humans. Monthly lunar cycles influence marine life through tidal patterns and may affect reproduction in some species. Annual seasonal cycles drive migration, hibernation, flowering, and countless other biological processes. Human cultural and religious calendars attempt to track these cosmic rhythms, with days measuring Earth's rotation, months approximately following the lunar cycle, and years tracking Earth's orbit around the Sun. Ancient monuments like Stonehenge and the temples at Chichen Itza were carefully aligned to mark solstices, equinoxes, and other astronomical events, allowing early civilizations to synchronize their activities with the cosmic clockwork. Some cosmic rhythms remain mysterious or contested. The solar system seems to pass through the galactic plane every 30 million years or so, which some researchers have suggested might correlate with mass extinction events on Earth, perhaps by disturbing the Oort cloud of comets. While this hypothesis remains controversial, it illustrates how astronomers look for connections between different cosmic cycles and their potential effects on our planet. Another intriguing rhythm appears in the distribution of galaxies themselves. Studies of the large-scale structure of the universe reveal that galaxies are arranged in a cosmic web of filaments and voids, with characteristic distances between structures. This pattern preserves the imprint of sound waves that propagated through the early universe, creating a fundamental harmonic scale in the cosmic architecture. This cosmic harmonic, known as the Baryon Acoustic Oscillation Scale, measures about 500 million light-years in today's universe and serves as a standard ruler for cosmologists. It represents perhaps the most fundamental rhythm in the universe's structure, a frozen echo of the sound waves that traveled through the primordial plasma before the universe became transparent to light. As we observe these various cosmic rhythms, from the fastest quantum oscillations to the slowest galactic rotations, we're essentially listening to the universe's heartbeat at different scales. Each cycle reveals something about the physical processes that drive cosmic evolution, from nuclear fusion powering stellar pulsations, to gravity orchestrating planetary orbits, to dark energy accelerating the universe's expansion. Modern astronomy has transformed the poetic notion of the music of the spheres into a precise science of cosmic periodicity. By measuring these various rhythms with increasing accuracy, astronomers can test theories of stellar structure, planetary formation, galactic dynamics, and cosmological evolution. Each cycle, each periodicity, provides a constraint that our models of the universe must satisfy. For all the cosmic rhythms we've discovered, many more likely remain undetected, cycles too subtle or too slow for our current instruments to measure. As observational techniques improve and observational baselines extend, we'll undoubtedly discover new periodicities, new patterns, new movements in the cosmic symphony. The study of cosmic rhythms also has practical applications. Pulsars serve as galactic clocks, potentially useful for deep space navigation. Understanding solar cycles helps predict space weather that can affect satellites and power grids. Knowledge of asteroid orbital periods allows us to calculate potential impact risks centuries in advance. Perhaps most profoundly, cosmic rhythms connect us to the universe across time. When we observe a Cepheid variable star pulsating in a distant galaxy, we're witnessing a cycle that has continued uninterrupted for billions of years and will continue long after we're gone. When we measure the cosmic microwave background's temperature fluctuations, we're detecting the frozen rhythm of sound waves from the universe's infancy, a 13.8 billion-year-old echo of the cosmos's earliest moments. These persistent cycles give the universe a kind of temporal structure, patterns that repeat across the aeons, despite the overall increase in entropy and disorder. In a cosmos trending toward heat death, where disorder generally increases with time, these rhythmic processes represent islands of order and predictability, cosmic metronomes ticking with remarkable precision across billions of years. The symphony of cosmic rhythms reminds us that we exist within a dynamic, pulsating universe, not a static or chaotic one. From the spin of electrons to the rotation of galaxies, from the daily cycle of sunlight to the billion-year dance of galaxies, we are surrounded by and composed of matter orchestrated into countless overlapping rhythms. A grand cosmic composition that began with the first moments of the Big Bang and will continue in ever-changing form into the far future. What remains when all the echoes fade? As we reach the conclusion of our journey through the universe's many whispers, it's worth pausing to contemplate the profound silence that will eventually envelope all existence. But this silence is not empty. It is full of meaning, rich with the memory of everything that has ever been. The universe began in a great rush of light and heat, and ever since it has been cooling, stretching, echoing, from the searing plasma of the Big Bang to the first atoms forming in the cosmic dawn, from the ignition of the first stars to the assembly of galaxies, from the birth of planets to the emergence of life. Each stage has left its mark, its echo, continuing to reverberate through the fabric of existence. Every particle in the cosmos hums with ancient history. The hydrogen atoms in water molecules formed minutes after the Big Bang. The carbon atoms in your body were forged in stellar furnaces that exploded billions of years ago. The iron in your blood came from supernovae that scattered their contents across space before our sun was born. You are, quite literally, made of echoes, stardust assembled into consciousness, able to perceive and wonder about the very universe that created you. Even the empty space between galaxies carries information about everything that has happened since the beginning of time. Gravitational waves from ancient black hole mergers still ripple through this space, stretching and compressing it by infinitesimal amounts. The cosmic microwave background radiation fills every cubic centimeter, a direct echo of the moment when the universe first became transparent. Neutrinos from the earliest nuclear reactions still stream through the cosmos, barely interacting with matter, but carrying their ancient message forward. As you sleep tonight, know that you rest in a universe of echoes. The darkness of your room is filled with photons that began their journey when the first stars shone. Your body contains atoms that have existed since before Earth formed. The air you breathe has cycled through countless living things over billions of years. Nothing is truly new. Everything is recycled, repurposed, reborn from the cosmic materials that have existed since the universe began. And what of the future? We've explored how the universe will gradually darken as stars burn out and galaxies recede beyond our cosmic horizon. How black holes will slowly evaporate, releasing their stored information in barely perceptible whispers of Hawking radiation. How even protons may eventually decay, dissolving the very building blocks of matter. How the final state of our universe might be an almost perfect vacuum, with only the occasional quantum fluctuation disturbing the silence. But even this silence will be meaningful. It will contain the encoded history of everything that came before, preserved in the precise arrangement of whatever particles remain, in the exact pattern of quantum fluctuations, in the subtle structure of space-time itself. Nothing will be truly lost, merely transformed beyond our ability to recognize. Perhaps most remarkable is that in this universe of echoes, we briefly exist as conscious observers, able to detect, measure, and understand these ancient signals. Through science, we've learned to read the cosmic story written in light and gravity, in atoms and particles, in radiation and space-time. We've become interpreters of the universe's many languages, translators of its whispered messages. This conscious awareness is itself one of the most extraordinary developments in cosmic history. Through billions of years of evolution, the universe has organized some of its matter into structures complex enough to contemplate their own origins. We are the universe becoming aware of itself, the cosmos reflecting on its own existence. This self-awareness may be rare and fleeting on the scale of cosmic time, but it represents something profound, the universe not just echoing, but listening to its own echoes. Sleep now, knowing that even the silence is not empty. It is full of whispers, full of echo is still traveling through the dark. And perhaps, in that quiet contemplation between wakefulness and dreams, you might sense your connection to this vast, ancient, ongoing story. You might feel for a moment how you are both made from and part of these cosmic echoes, these whispers across time, these memories of a universe that has been evolving and communicating since the very beginning. For we are not separate from these cosmic processes, but integral to them. Our atoms will eventually return to the stars. And whatever consciousness or understanding we achieve, whatever art or science or wisdom we create, becomes another echo in the grand cosmic symphony, another whisper that joins the countless others still traveling through the dark.